Good year, sir.
हाँ सर, वी आर गोइंग टू स्टार्ट इन जस्ट 1 मिनट।
आवाज आ रहा है ना बराबर?
हाँ बराबर आ रहा है, आ रहा है, कोई प्रॉब्लम नहीं है।
You want to use the screen? No, you want to use the screen. I want to open my PPT.
Will you be sharing that PPT? Share.
No, not now. When my turn comes.
Okay, so that in that case, which is Alt, advi tab adu. Alt, tab adu. Or the press go. Then you press tab. You can switch between.
First open the. Let me open it now.
Open Alt PPT. Okay.
Good, sir. Good, sir.
Yes.
Yeah. Hello.
I think everything is ready, so we can start now.
No, sir, Rangaswamy sir is, I think, he's taking trial.
Okay. Just confirm with Rangaswamy sir, then immediately we'll start.
Video on, correct? हाँ sir, Professor Rangaswamy, are you ready? Are you there? Hello.
Yeah, I am here only.
Sir, shall we start, sir?
Yeah, we can start.
We can start, Okay. Rabhi madam.
Yes, sir. Namaskar. Very good morning to one and all. Honorable Director of DKTE Society's Textile and Engineering Institute, Professor Dr. P.V. Kadole, Head of Department of Textiles, Indian Institute of Technology, Delhi, Professor Dr. R.S. Rangaswamy, eminent speakers from India and abroad, Deputy Director of DKTE, Professor Dr. U.J. Patil, Convener of Conference, Professor Dr. M.Y. Gudiavar, Professor R.L. Gotipamul, faculty members and all the participants. It gives us immense pleasure to welcome you all for virtual international conference on innovations in textiles, products and processes, that is ITPP 21, which is being held today and tomorrow. The conference is starting with inaugural session followed by technical session. All the eminent speakers will blossom the knowledge and we will enjoy the learning. So let us start with inaugural session. For this, first of all, we would like to request Professor M.Y. Gudiavar to brief about the conference. Please, sir.
Very good morning to one and all. Professor P.V. Kadole, Director, DKT's Textile and Engineering Institute. Professor R.S. Rangaswamy, Head of the Department, IIT Delhi. Professor U.J. Patil, Deputy Director, DKTE. All the speakers, participants who are present in this conference. Thank you for joining us today on the virtual international conference on innovations in textiles, products and processes. It is my pleasure to welcome all the participants for the two-day international conference. This conference is completely conducted on digital platform due to the COVID-19 pandemic, and conference has a very unique theme which is relevant to what is happening to the world in 2021. The concept And theme of this conference is Innovations in Textiles, Product Design, Process. The conference is designed to disseminate the latest research findings and advances in the textiles to academicians, scholars, technocrats of industries, and researchers from R&D organizations, specifically focusing on innovations in textiles, product design, process. Today's conference has more than 500 participants participating from different countries and invited speakers from 7 countries, making this conference a truly international, and we have left no stone unturned to make this conference a truly international conference. The keynote address for this conference will be delivered by eminent academician and researcher, Professor R.S. Rangaswamy of IIT Delhi. The invited speakers are renowned academicians, researchers, and technologists from reputed universities, research institutes, and industries, and they will share the research and development activities. I request all the delegates and participants to attend all the sessions and take active participation in the conference. I wish everyone a successful, safe, and fruitful conference. Thank you.
Now we will have speech by Professor Dr. P.V. Kadole. He is the director of DKTE Society's Textile and Engineering Institute. He has completed MTech from Anna University, Chennai, and PhD in Textile Engineering from Shivaji University, Kolhapur. He is having more than 30 years of teaching and industrial experience. His area of specialization are spinning and product development. He has authored 6 books. He has published more than 150 research papers in national and international journals and presented more than 60 papers in national and international conferences. He has carried out projects, consultancy assignments for industry in the area of textiles. He has guided more than 100 MTech and PhD textile engineering students. He has been felicitated with many prestigious awards and academic recognitions. With this, we request Honorable Director of our Institute, Professor Dr. P.V. Kadole, sir, for welcome speech. Please, sir.
Yeah, thank you. Very good morning, one and all. I wish a warm welcome to everyone to this virtual international conference on innovations in textiles, product and processes. Professor Dr. Rangaswamy, who is the head of textile department of IIT Delhi, a very eminent academician, who is the keynote speaker for today's inaugural function of this international conference. At this moment, all the learned speakers who are present online to this activity from various countries, my fellow colleagues from textile department, faculty members from various engineering colleges, my student friends, and even there are participants from industry. A warm welcome to you all. So, as said by Dr. Gudiavar, it's a virtual conference. We would have been very happy to see you all at DKT, but this pandemic situation has not allowed us to conduct the conference in physical mode, and therefore we are now assembling here in an online mode. Before we proceed further, I would like to dwell here for a couple of minutes about my institute, which is called as DKT, but normally it is DKT Society's Textile and Engineering Institute, which was started way back in 1982. It is a first of its kind to be started on unaided principles in the state of Maharashtra. Very inception of the institute goes in like 9 industries. They came together and they incepted this institute, and therefore right from inception, right from beginning, we have got industry culture in the institute, and therefore we have pursued this a very intensive interaction with the industry in various ways, like consultancy, like troubleshooting, like even calling eminent technicians for conducting lectures at our institute. And really it has paid in a huge way, you can say, to DKT, because at the moment, sir, we have more than 16 industry sponsored laboratories in our institute. And you can name any machinery manufacturer in the world, they have donated their state-of-art machine to our institute. And therefore, we are very fortunate, our faculty members and our students, to work on this machine. They get hands-on experience on this machine while working in the institute. And this has helped in getting a very good placement. And every year it's 100% placement for our textile students. And normally they do go into the textile industry only and not into the softwares. And at the same time, there are international placements also. In 2016, so we got autonomous status to our institute, and therefore we could craft our own syllabus, and we could include in the syllabus the industry sponsored electives also. Not only that, there is what is called as really credit transfer system which is happening at our institute, because we have signed MOU with different 24 foreign universities, and in some of the universities we have started credit transfer program also. Some of our students, they go to these foreign universities for one entire semester. They stay there for one entire semester and they take up courses there in those universities, and they earn credits there, and these credits are transferred once they come back and join our institute in 7th semester. And this has really helped even this MOU with the foreign universities for internship of our students. Every year around 30 to 35 of our students, they go to these foreign universities for conducting internship for 4 weeks, 5 weeks or 6 weeks. And this has really widened their horizon of thinking about the textile activities that are taking place in those countries. And not only this, sir, this has really given an academic ambience to our institute. And this has also helped our institute to garner support from different ministries, because we have got very good sponsored projects from different ministries like Ministry of Textiles, Ministry of Industry, even from Department of Science and Technology, from DRDO, like that. Very prestigious projects like TIFAC Core in Technical Textiles, Technology Business Incubator Center in Textiles from DST, and Center of Excellence in Non-Owns from Ministry of Textiles. So all these projects are running on very well in the institute, and students and faculty members are taking use of it. And really this has given a very good ambience, and all the programs of our institute are NBA accredited, and NAC also has accredited our institute with the scale of 3.53 out of 4. Recently, sir, we have got QIP Center for PhD in Textiles, in Computer Science and Engineering, in Electronics and Telecommunications Engineering, and in Mechanical Engineering also, which is given by AICT. And very recent announcement of AICT is that our institute has got AICT Idea Lab, which shall be very helpful to our students to incubate their ideas, and they can come out with some product development also. And really it is helping for many startups, and I'm very proud to say that more than 500 of our alumni, they are working as entrepreneurs in textiles alone. And this would have been better had it been a physical mode, this conference. I would have been very happy to show you all these facilities that are available at DKT. Nevertheless, once this pandemic situation is over, I shall be inviting all the renowned scientists, the renowned speakers, and all the fellow faculty colleagues from various engineering colleges to come down to our institute and give us an insight, and give us, in case if there are any lacunas or any loopholes in our institute, so that we will try to overcome in all this, because we want to excel in academics. I'm very thankful to Dr. Rangaswamy, who has kindly considered to our request to join this conference for giving keynote address, and I shall be listening to him in this conference. So once again, I welcome everyone, and thank you everyone, and wish you all the best for this conference. Thank you.
Thank you so much, sir. Now we will have keynote address by Professor Dr. R.S. Rangaswamy. Professor Rangaswamy is Head of Department of Textile Technology, Indian Institute of Technology, Delhi. He has completed his master's degree from PhD Coimbatore and PhD from IIT Delhi. His area of specialization are extreme cold climate clothing, oil spill cleanup, mechanics of textile structures, thermal, moisture and liquid transport in textiles, garment technology, etc. He has authored 8 chapters, 2 books, 2 monographs, and has published more than 100 papers in various reputed journals. He has presented more than 50 papers in conferences and more than 30 presentations in conferences, seminars, and workshops. Such a knowledgeable personality is available with us today. We request Professor Rangaswamy sir to deliver the keynote address. Please, sir. We request you to share your presentation.
Thank you.
Thank you, sir.
Are you able to see my screen?
Yes, sir. It's visible.
Good morning to everyone. First of all, I have to express my thanks to Professor Gudiabar, Professor Kadole, and UJ Patil for asking me to give a keynote address. It is my privilege to give a keynote address in such a big conference. I have visited DKTE Institute 2 years back, and really was, we didn't have much idea because they are a good institute. But when I see the facilities, I felt a little bit jealous that some of the facilities we don't have in IIT Delhi, especially in the area of non-movements and other things. So we tried to have some joint project, and due to some reasons, it didn't go. But still, we have the options to continue because of some changes in the COE. So when I was asked to give a topic, give a keynote address, so I was thinking about the theme of the conference: innovation in textiles, product and the process. Innovation is always a part of the human evolution, and every animals, birds, plant, they always try to innovate so that they're able to sustain the environment, able to adjust themselves. Since I am working in the area of extreme cold weather clothing, I read a lot about the insulation material that we get from the down material. The down is basically a material we extract from elder, goose, and duck. Apart from the the feather, they also have this goose. So I was wondering how these birds, they are able to survive in -40, -60 degrees centigrade, and what the unique the geometry of the material, and what is uniqueness about the mechanism of the material in able to retain the insulations. So that motivated me to choose a small topic on down nature's innovation to sustain extreme cold climate clothing. We have to always observe what is happening around, and so that we get an idea that how the plant, the birds are having this technology, and whether we'll be able to mimic this one for our daily lifestyles. So when you see the down material is attached to the skin of the bird, that is the plum, and from the plum you find a lot of barbs, going in all the 360 directions, primary structures. From the bar you will find the barbulous number 2, which I indicated. They also go in all possible directions. And the enlarged view of the barbulous is given here, and you can see it is suddenly the cross section turns into triangle, and it is very beautiful symmetrical material. The barb and barbulous, if you are able to measure the, the orientation of the fibers or orientation of this one, you will get all possible directions, perfectly symmetrical. I don't think we have any such material, we developed, which is, perfectly symmetrical. You can see the, from the core plum, the bars are branching out in all possible directions. And the beauty of the, the cross section of the bar are triangular, not only triangular, they also hollowness. They are hollow. And the diameter of the barb is around 20 micrometer, and they live in all possible directions. When you see the human, from the human body, we have radiative heat loss. The radiative heat loss is basically through the IR waves, the skin is emitting. The IR waves coming from the human body is from 5 to around 7 micron to 15 micron. So whenever the IR rays hits the barbs, it will be reflected or it will be absorbed. When you see the barbless initially, it starts in elliptical cross section, and it is a solid, and also it goes in all possible directions. I'll come back to this one, why it is elliptical. And in each barbless, we have 3 to 4 nodes. The nodes are in triangular cross section. The unfortunate thing is, they try to retain more moisture. And if you try to make a clothing out of this one, and when there is a lot of soot is there, it is very difficult to dry. But in the case of birds, when they also dip into water and simply they throw the water out by shuttering the feathers, which is not possible for us, because in the government in Sambal, the everything is enclosed. So when you see how we are using this now, the goose down for the insulating materials. Of course, now we are we are moving away from the goose down because of the availability of non-availability of materials, and we have to kill a lot of birds. Plus, they have the very high moisture absorptions. When they have high moisture absorptions, they lose the insulations. So now we are trying to develop synthetic materials, substituting the synthetic materials for the down materials.
Hi, na?
So human body has to be in thermal balance. Whatever the heat we generate, it has to be equal to the the heat lost to the environment. So that should be balanced from the left side to right side. So the heat lost to the environment from the human body is through conduction, convection, radiation, respiration, and evaporative. So one has to perfectly balance this one, and that comes the extreme cold weather clothing or extreme cold weather jacket. So when we are not able to have proper insulations, our human body core temperature falls below 32 degree, and slowly it goes to 28 and below that. So many of us will survive up to 32 degrees centigrade, and few of will die when the temperature goes below 28. So we have a lot of frostbite, broken, cracked skins, all things. So when you have want to develop the insulation material, what is the main criteria? We want to have more insulation with less weight. So that means the warmth to weight ratio has to be higher. And the insulation, what we get today, has to be retained even after 6 months. Because when you are wearing the jacket is being compressed. And over the period of time, what happens? The material may get compressed. They may lose the thickness. When this happens, the the jacket will lose its insulations. And of course, we need to have water resistance. Now coming to the interesting point about how the goose down is giving insulation from the when you look at the science of physics, conduction, convection, radiation. When you apply, when you go through all these concepts, the goose down is giving solutions. We know that heat is lost through conduction, heat is lost through convection, and heat is lost through radiations. How the goose down has developed a structure which is trying to reduce the conductive, convective, and radiative heat loss. Then later I will coming to the mechanical aspects, how they are going to retain their insulation in terms of resiliency. The first thing is you try to reduce the conductive heat loss enormously to a large extent. The thing is that the barbs are triangular cross section with hollow, so they also entrap the air. Since there is large number of barbs and barbless in all possible directions, barbless are very fine, one. Barbs are around 20 micron diameter. You can imagine about 4 linear polyester fiber. So barbs are around 4 linear polyester fiber. It's a triangular hollow polyester fiber. So large number of barbless are there, very fine barbless in all possible directions. When the air is entrapped, air cannot move easily. So they entrap the air, and that through which convective heat loss is minimized. And because of the unique structures, they generate more volume. So that means the solid volume is less than 1%, only 0.5%. 99.5% is only the air. So air gives better insulation. So the overall the conductivity depends on the conductivity of the solid materials and the conductivity of the air. And because of that, the conductivity of the filled goose down is very low. I don't think any synthetic material is near to this one. Then coming to the radiation, and when the body is not a human body is not flat, it is a curvature, it is curved one. So when the IR waves are coming from the body, it is all the direction, 360 degree directions. So the possible way of preventing the radiative heat to go out of the body is to reflect the IR waves, and this is done by the barbs and the barbless. So large number of barbless in all the 360 directions, plus the large amount of surface area, they always try to prevent the radiative heat loss going out. Either they absorb or they are able to reflect. So there will be a lot of total internal reflection of the IR waves between the barbless. So effectively what happened, the conductivity of the goose down is very low. Conductivity loss is almost zero. Radiative heat loss is almost zero. Now coming to the mechanics aspect, how they're able to retain their compression. So when you look at the compression behavior, when you compress the material, okay, there is no buckling and purely the yield stress, the elastic modulus is going to decide about how much resistance it is going to give. If the material is in a straight in Z directions, and the material is somewhat flexible, then it may go under buckling. In all the cases, if the free length is more, what happens? It will end up going for yield. It goes for buckling. So buckling is little easier than the compression. Now, when you imagine the goes down 360 degree dimensions, so there are many places they are locked, and the free length what you get will be very low. So the buckling load will be very high. So what is the difference between our non-woven, thermal bonded non-wovens now we are making as a replacement to the goose down? Our non-known materials always in XY directions. Hardly less than 1% of fiber may be in the Z directions. Whereas if you see the goose down, it is 360-degree directions. So there comes the difference. We are not able to make a fiber, okay, where all fibers of nearly 4 linear attached to one place. And from each fiber, there is a branching. And then each branching, you have, nodes. So it's very difficult to innovate these materials. So let us see how they offer resistance against the compression. As I told, the material, the bar, the coarsest one in the goose down is the bar. Barbs are hollow triangle. And if you see the mechanics, the triangular one for a given linear or given cross-sectional area, the triangular one is giving always 20% more bending rigidity than the circular one. So the bar tried to give more bending rigidity. In the process, it tried to retain its thickness. Second thing is, the barb is not only solid triangle, it is a hollow triangle. When you see the area moment of inertia of the hollow triangle and the solid triangle, the hollow triangle gives 35% more bending rigidity than the solid one. So imagine if you have a circular solid polyester fiber, in some circular fiber, you try to make a hollow, the triangular fiber. The hollow triangle fiber of the same linear will give 65% more bending rigidity than the solid circular fibers. So that is the beauty of the structure of the barb. Then the barbless is elliptical cross section. As you see the mechanics, the ellipse have major axis, minor axis. The bending rigidity with respect to the major axis is lower, and the bending rigidity with respect to the minor axis is higher. And the material is constrained between barbs and the barbless. It will try to rotate in the favored configurations. That means the lower bending rigidity. So when you try to compress, locally it will bend with respect to the major axis. So when you try to compress it, what happens? The nodes from one barbless and the nodes from the other barbless, they touch each other at the nodes where the area of contact is very high. So what happens? Literally, they lock. One barbless will lock the other barbless. So don't expect that both the barbless are in vertical direction. When they are meeting, they will be in all possible directions. So when you compress, it is not pure compressive, it is pure bending. It is both bending, compression, and torsional energy. So when you see something is vertical, we will apply a load. It is purely a compressive load. And it can buckle also if the free length is more. When you apply a load onto a horizontal beam, there is a deflection. The deflection is related to the bending rigidity of materials. If there is a hollow material, deflection will be very low. If it is hollow and triangular, still deflection will be lesser. Now, if it is a material is not in the Z direction, not in the XY direction, but it is all the directions. Imagine like a spring. So when you apply load onto a spring, so no part of the fiber is vertical. It is somewhere between vertical to the horizontal axis. So it will undergo bending as well as torsion. So in the case of goose down, what happened? There is a node, it is locked, and there is another node which is locked, and that is a free length. And the free length is not in the Z direction, not in the XY directions. So when you apply a load, what happens? It will undergo both bending as well as the torsion. So the torsional energy, bending energy is stored when you apply a compressive load. The moment you remove the load, the torsional energy and the bending energy, even the compressive energy stored by the material will help in recovery of the materials. So that is the beauty of the goes down material. The challenge is main thing is now it is having more moisture absorption that I will come later. Now, can we mimic this goes down? So far, we are not able to mimic. The only thing we are able to mimic is you have a fiber which cream, which is helical cream. This is the only thing we are able to do it. And instead of solid fiber, we are able to make a hollow fibers. But how you can but all the fibers are in the XY direction. When you make nano ovens, fibers are spread and laid in the XY directions. And only a small part of the fiber, because of the configuration, they will be lying in some Z directions. So if the cream is not like this, cream is like a regular cream, it is predominantly in the XY directions. If you try to create cream like this, it may be to some extent, you are promoting the segment of fiber in the Z directions. So through which we will be able to improve the compressor resilience, and we are able to improve the space filling capacity of the fibers. So with this, let me conclude. We have to always look at nature. You see how the leaves having nano scale roughness. So this is a very unique 3D structures, and it has all the features of controlling the conductive, convective, and radiative heat loss. And you apply all the physics, it gives the solutions. And if you see the mechanics of compression, bending, and torsion, and it has everything. And the question is whether we'll be able to develop this one. I don't think we'll be able to develop a fiber which is three-dimensional. So we have to look for some other route where the individual fibers are laid in a particular way, like 3D nano ovens. But how we are able to get nearly 99.5% porosity, that's a great thing. With this, let me conclude. And again, I thank you, DKST Society for Textile Institute, choosing me to give the keynote address. So, wish you all the best.
Thank you so much, sir, for exploring information about applications of goods down in extreme cold clothing. Now, I will share the PPT, sir. I request you to stop this PPT so that I can share. We will have the vote of thanks by Deputy Director of our institute, Professor Dr. U.J. Patil, sir.
Yeah.
I request, sir, to please.
Good morning. A warm greeting to all the dignitaries, delegates, and student friends. On behalf of DKT's Textile and Engineering Institute, ICHALKARANJI, India, it is my immense pleasure to express my gratitude on this memorable occasion of virtual international conference on innovation in textile products and processes, ITPP 2021. When 8 months ago, the plan of organizing international conference was discussed in the department, then we had taken a decision to go for invited paper rather call for papers. Subsequently, when we contacted at international level researchers, then almost everyone agreed to participate in the conference because of DKT's strong rapport with them. Consequently, today and tomorrow, conference will be held with 11 excellent research presentation. And for this conference, we have received overwhelming response from delegates from industry, research laboratories, even from India abroad. Firstly, I express my deep gratitude to our chief guest, Professor Dr. R.S. Rangaswamy, Head of Textile, IIT Delhi, for accepting our invitation and addressing gathering with keynote address. Thank you, sir, for joining us from your busy schedule. I am very much delighted to express thanks to all the researchers, presenters, Professor Dr. Rajesh Mishra, Dr. Ashok Rajpurohit, Professor Dr. Nico from Hop University, Germany, Jan Thiel, researcher from RWH Aachen University, Germany, Professor Dr. A.K. Patra, head CCTI Kanpur, Professor Dr. Ram Kumar Sheshadri, Texas Tech University, USA, Professor Dr. Ayub Nabi Khan, Pro Vice Chancellor, BGME University, Bangladesh, Professor Dr. Manas Kumar Sarkar from Hong Kong Polytechnic University, Hong Kong, Vinay Karulkar, BW Tech India Limited, Martin Pelzer, Research Asset from RWH Aachen University, Germany, Professor Dr. Pratik Goswami, Professor in Technical Textile from Textile Research Center, University of Heidelberg, UK. I would like to thank all our beloved dynamic director, Professor Dr. P.V. Kadole, for his continuous guidance and encouragement for this memorable happening moment. I also thank to all the delegates from industry, university, research labs, alumni for their presence to this conference. I also thank to my colleagues, my student friends for their presence to this conference. Thank you all once again. Thank you.
Thank you, sir.
Over to Raibhag. Yeah.
Thank you. Herewith, we declare that the inaugural session is over. We are going to start with the technical session day 1. Speakers will complete presentations in 25 minutes and 5 minutes will be there for question and answer session. Participants are not directly allowed to ask the questions. Instead, they are requested to post their questions in chat box. Day 1, first technical presentation in the conference is by Professor Rajesh Mishra. Before that, I would like to introduce sir. Dr. Rajesh Mishra is professor at the Czech University of Life Sciences, Prague, Czech Republic. His research areas are textile structural composites, biomechanical engineering of fibrous structures, and thermomechanical characterizations of materials, etc. He has about 170 publications in international journals and about 300 presentations in international conferences. His teaching and research activities include subjects based on nanotechnology, biomaterials, textile quality characterizations, engineering of textile structures, etc. He has also developed educational and research cooperation with many organizations around the globe. His topic of presentation is nanotextiles, past, present, and future. With this, I request sir to please start with his presentation.
Thank you very much for kind introduction and very good morning to everyone. I'm thankful to the organizers, especially Professor Kadole sir and Professor Patil and all the faculty members of DKTE who have been in constant cooperation with us. Since time is little short, let me straight away start with my presentation. Today's discussion will be nanotextiles, its current status and what is way ahead. In fact, nanotechnology is an emerging area of research and innovation. So we are looking at a sustainable society, sustainable future. And the sustainability of our future, as far as industry, technology, and environment is concerned, it depends on 3 major aspects. I have classified them into environmental factors, factors influencing energy. Energy is one of the major concerns in modern day world because we are struggling with shortage of fossil fuel, and we need to look into alternative sources. And we need to minimize the wastages and effectivity of the cost, and which is very much in the field of economy. However, today's discussion will focus mainly on environmental aspects and the crisis of energy, how they can be dealt with by adopting nanoscience and technology. So focus will be mostly nanotechnology, nanomaterials, and more that of textile application. So here are a few of several challenges that the current world is facing, and in future we need to be prepared to combat such situations. Pollution, one of the major concerns, and we need to minimize this human created pollution. It can be with respect to air, water, noise, we have an acute shortage of energy, and we need to conserve energy. We need to minimize the wastage, and if possible, to use alternative sources of energy rather than polluting sources. And we are dealing with extreme psychological situation of humans all over the world. There is war, there is terrorism every now and then. We need to prepare protective systems so that the people who are involved into this kind of a situation, they are protected. And as such, we are passing through 2-3 year long pandemic, and several probably could be there in the future, and we need to prepare ourselves for that. And as such, medical extreme situations, they do exist. So through innovations in nanotechnology and nanotextiles, we'll try to solve some of these problems to a certain extent. Nature is mother of all innovations, and always we take inspiration from nature. As far as nanotechnology, nanoscience is concerned, it has been in nature always in everyday life. If we keenly, minutely look into several natural phenomena, especially plants and animals, or even insects, we can observe extraordinary features which are the result of nanomaterials, nanostructures, nanoscience. Some of the insects, they have such submicron and nano corrugations on the surface of their body that it is dust free. It never gets dirty when they enter into soil, come out of soil, which is practically not possible in human activities. The frictional force which holds a child on the surface of the mother is the result of specific surface area, huge specific surface area, which is due to the nano features on their scales and palms. We have always experienced extraordinary combination of colors in the butterfly wings, and these colors are not due to pigments, they are due to interference of light waves, visible light waves, and the interference generates several brilliant colors which are not due to any pigment on the surface of the wing. And such phenomenon is mainly due to the nano feathers in the butterfly wings. Through research, it has been possible to replicate such kind of a color spectrum by sonochemical technique, by creating nano surfaces, nano features, and we have been able to develop interference of light and create color effects. So this is one of the very innovative and non-polluting method to have color effects, because we are not using toxic color pigments. However, how broadly it can be used is definitely a question. Super hydrophobicity observed in very fine insects, especially mosquitoes and some flies, enables them to stand on surface of water. You must have observed that the mosquitoes don't need to swim; they can easily stand on surface of a pond water. And how is it possible? It is because of the very fine structures on their palms, and these structures are in nano level, so that they have very huge specific surface area and very high level of surface tension, reducing the surface tension, improving super hydrophobicity and ability to stand on water. That is why they are called as pond skaters. Lizards or such creatures in nature, they can walk upside down, they can defy gravity, and they can move on vertical surfaces. And this is mainly because of the nano features on their palms, which are renewable. Especially when we try to replicate these kind of things in artificial way, we are not able to remove the dust which gets accumulated. We are not able to renew their surface area. That is the problem. Otherwise, in nature, they have inherent ability to clean the surfaces of nano features on their palms, and which enables them to have very high level of friction, which is necessary for walking against gravity. To some extent, we have been able to replicate the effect of shark skin. Sharks are sea animals, sea creatures, which can swim at a very extremely high velocity. And this ability is by reducing the friction with water. And this reduction is by specially oriented nano channels on their skin. To some extent, researchers have been able to create such channels on the swimsuits of Olympic swimmers, and their performance has been enhanced by a few seconds. Even that is very important as we witness in such world events, and such things are slowly getting into practical application. One of the major structures in nanoscale are known as nanofibers, where the dimensions, especially the diameter, is in few nanometers. As per the classification of nanomaterials, the diameter should be less than 100 nanometer. The technique that is used to produce the nanofibers is called electrospinning. It is not by melt spinning or solution spinning. It is by use of electrostatic field, and we need to have very strong electrostatic field of the order of 10,000 volts between the nozzle or the generation point and the substrate or the collection point. And this distance and the voltage that decides what will be the diameter of the fibers, especially the diameter is not uniform. Why? Because we are not having any positive control over the diameter by stretching or drawing as in case of conventional spinning, but it is just random deposition of fibers. That is why the diameter may range between a few nanometer, less than 10 nanometer, to some 100 nanometer or 500 nanometer. And thus, the variability of nanofibers in this method is definitely a matter of concern. It can be minimized by consistent viscosity, concentration, voltage, and the distance of between the two electrodes. The previous slide which showed the needle electrospinning is only for small scale research in laboratory scale. However, if we want to produce large scale nanofibrous material, we need to have a series of needles either, or to have a cylinder, kind of cylinder in a bath which collects due to rotation a thin film of polymer solution. Why I call polymer solution? Because the solution is not temperature dependent, not that much dependent on temperature like molten polymer. Molten polymer could be electrospun, but they solidify very quickly. We cannot have constant heating. That is why in electrospinning, mostly solvent spinning or polymers which can be soluble to some solvent, they are preferred. So a film comes to the surface of this cylinder, and from the surface, several so-called Taylor cones are generated, which are splitted into fibers, and we are able to cover any surface of fabric, already existing fabric or yarn or paper, with a mat of or membrane of nanofibrous material. Nanofibers can be produced from natural polymers, especially some researchers try to produce nanofibers from silk fibroin, from cellulose, and they are biodegradable. They are less polluting. Electrospraying is very similar to electrospinning, but it doesn't form fibers. It only forms a porous, more of nanoporous membrane by deposition of these droplets. How is it possible? If we reduce the concentration of the solution and thus don't allow the solution to be converted into some tubular fiber-like structure, but just split it into very fine droplets which are deposited onto a substrate, and these droplets create a membrane which has the same level of porosity and features like the nanofibrous material, and it is easier to form, and they have the same level of filtration efficiency and permeability as nanofibrous membrane, and easy to form. That is why in many cases it is better to adopt electrospraying rather than electrospinning. In Czech Republic is a company named Elmarco, which is producing industrial scale Nano Spider. They call it Nano Spider because it spins the nanofibers, and they are able to produce like laboratory model, industrial model for large scale production. And we must be thankful to these and other companies around the world who have produced and supplied several tons and billions of tons of nanofibrous membrane in the pandemic era, because we know that the mask that is used, especially N95 mask, FFP2 masks, they are all having multiple layers of textiles or nanowovens especially, and the middle layer or the functional layer is definitely a nanofibrous layer. And this nanofibrous layer has porosity in the range of very fine dimensions, especially nano dimensions, so that it doesn't allow the droplets containing the virus virus to pass through. And if we are in an infected environment where the virus is moving around in the atmosphere, it doesn't pass through the mask, and we are protected. Similarly, masks in all medical applications, they have nanofibers being used. Nanofibers based filters are used for air conditioning. They are used for oil filters, because oil, especially petroleum, sometimes needs to be separated from other kind of liquids. Maybe if it is spilled on surface of ocean, we need to separate from water. Nanofibers are extensively being used for tissue engineering, especially for repair of bones and muscles, because they provide the surface area required for rapid growth of tissues. They themselves do not heal, but they provide the platform for the tissue growth. We can find in literature several articles where people have demonstrated the rapid growth of tissues on the surface of nanofibers or nanostructured membranes, or this kind of substitutes for the muscles. Human skin is very complex system. It also has multiple layers, and it is basically selectively permeable. It doesn't allow everything to pass through. So similarly, some features have been engineered into nano membranes, and they are used for skin repair, and also for bone repair. So as we saw, there are several possibilities to use nano materials, especially in medical field, for healing of wounds and repair of bones and tissues. One of the major materials are composed from carbon. Carbon is very important element in our world, because it has very high level of conductivity. And it is possible to use carbon in many forms. Some of us may be aware that carbon nanotubes are considered to be one of the strongest materials, though the dimension is very small to be used in practical fields. However, it is really very strong with respect to its modulus, and carbon nanotubes can be used as a filler in composites to enhance the surface area and the interface between the matrix and the reinforcement, and thus they can improve the mechanical performance of the composite material to a very large extent. Apart from that, because they are composed only from carbon in very systematic fashion, they have very high level of thermal conductivity, electrical conductivity, absorb magnetic radiation, electromagnetic radiation, and such features are engineered into composites and coated textiles by use of carbon nanotube. A relatively easier method to produce carbon structure is by pyrolysis of acrylic to produce carbon nanofibers. Just pyrolysis is not enough for nanofiber formation, but it has to be ground and mechanically splitted to have nanostructures. Maybe all of them are not of the same length and same diameter, but they can be used as a substitute for carbon nanotubes. So the enhanced features of conductivity with respect to heat, electricity, and mechanical performance are definitely by means of using carbon-based nanostructures. Another very important and very interesting features of carbon nanotube is the channel. Carbon nanotubes are tubular structures which encapsulate water molecules inside their channels. Because my daughter was going to school, I interrupted the carbon nanotube can encapsulate water molecules, and we can absorb water from dry environments, because dry environments like in desert, they need water to be preserved, and we can release this water from carbon nanotubes at times of requirement. Particulate nanomaterials are more widely used in the textile field, especially for coatings, for reinforcement of composites, and we can have many engineered nanoparticles. There are many nanoparticles existing in nature. Some are unknowingly created by us, especially cigarette smoking. Cigarettes produce a lot of nanoparticles of carbon, and I'll come to that later on. How even the fumes, which are the exhaust of petroleum burning, especially in the automotives and the aircrafts, they produce nanoparticles of carbon. However, we create nanoparticles artificially in the laboratory to be used in composites and coatings. Other than that, we also have zeolites, dendrimers, and other kind of self-assembled nanostructures. The science of nanomaterials is very interesting because they do not follow certain laws of common physics and chemistry. In the nano level, the behavior of material changes and drastically as compared to macro level same material. Today's scope is not covering everything, so let me only focus on textile-based nanomaterials. Especially the nanoparticles of carbon are created from waste materials of textile, acrylic-based textile, because by pyrolysis of acrylic, we are able to create the nanofibers and nanoparticles. It is also possible to have nanoparticles from cellulose, waste cellulose fiber, for that matter, jute or any other fiber from plant, can be alkali treated to remove the lignin and other unwanted hemicellulose material. Then the pure cellulose, crystalline cellulose, because by this treatment the amorphous parts are removed, or the macrostructure is broken into micro crystalline structures, and further by mechanical action like cryogenic ball milling, it is possible to have nanofibrils or nanoparticles of cellulose. In some research, the nanoparticles have been used in polylactic acid composites, and the mechanical performance has been enhanced in nano level, micro level, macro level. There are techniques to measure the mechanical performance in nano level by so-called nano indentation, and nano indentation proves that the elasticity or the modulus of elasticity increases as we add up to 3% of nanoparticles. And to be noted that the nanoparticles used in such composites is limited to very small percentage by weight, as high as 5% maximum. And at the same time, they are able to cover the whole volume of the material very efficiently because of their minute structure, minute size. So it is not that 3% is too small, but they occupy the whole space, efficiently increasing the specific surface area and the performance thereby. So this is the device by which mechanically the nanoparticles can be created from macro materials, and I already explained about indentation. Indentation is commonly used in metallic industry. For polymers, they can like a very minute nanostructured indenter penetrates into the material surface, and the time required for recovery of this indentation mark shows how elastic is the interfacial bond between the particle and the matrix. Micro level mechanical properties can be analyzed by dynamic mechanical analysis, and the storage modulus was observed to be superior when nanoparticles are added to the polymer film. As such, macro mechanical property by stress strain analysis was also studied. Such nanoparticle field composites known as nanocomposites are used in agricultural field, especially for protection of delicate plants from UV light, and definitely from also mechanical performance is superior, so they protect the plants from any kind of damage. At the same time, the interesting feature is they are biodegradable, so it is not a matter of concern that they need to be removed every now and then. Nanocellulose based films or membranes are used for skin care, for UV protection, in medicine, especially because they have ability to dissolve in the intestine or the digestive system easily. So they are used as cover of the medicines. They are used for creation of cellulose-based aerosols. They are used for packaging of foodstuff, especially ready-to-eat food like meat and fresh vegetables. They must be covered in some package where they are selectively permeable. They allow the oxygen molecules to go through, but not toxic gases, and not allow UV light and other kind of hazardous wavelengths of light. So this nano porosity is very crucial to decide what amount of light will be allowed, what amount of gas molecule will be allowed, which size of the molecules will be allowed to pass through. On a larger scale, such nano materials, nano composites are used for certain components in the automotive industry, because now there is a transition to green materials, and especially companies like Skoda, Volkswagen, they try to adopt nano composites made from cellulose and polylactic acid to be used in some panels in the interior, because they don't need very high load bearing, especially in the interior. Other applications of nano materials are in coatings for flame retardancy, because they prevent the generation of toxic gases, especially some particles, and for skin repair, as I already mentioned. So for biomimetic and bioinspired membranes, nanoparticle filled structures are very widely being used or being projected for future use. Another interesting feature of nano structure is the so-called lotus effect. If we microscopically analyze the surface of lotus leaf, we see the bars or the projections which are very small, especially a few nanometers, and the distance between two adjacent projections is also less than 100 nanometer, and that enables the droplet of water not being able to be absorbed or spreaded to the surface. Artificially, if we are able to create such nanostructure on a textile fabric, we are able to have super hydrophobicity, and this is a story of the past. Already we have several super hydrophobic textiles by adopting such features, but this has definitely inspiration from the lotus leaf effect in nature. UV protection can be achieved by adjustment of the pores, so that the visible wavelengths of light can definitely pass through, but UV light doesn't pass, and this is by some coating of titanium dioxide based nano material, and we are able to have protection against UV light, though we cannot cover from head to toe, but some part of the body can be protected. We can use inherently antimicrobial materials in nanoscale, like chitogen, which is naturally available from sea animals, can be made into nanostructure by mechanical action, ball milling, and then we can use them into certain coatings and finishing, and thus having enhanced antimicrobial property by nanoscience. Nanoparticles, when dispersed into polymer films, they have very special performance, especially the distance between adjacent particles. In this picture, I am showing particle as a platelet. Platelet is a flattened structure, and let me tell you that platelets or flattened structures have enhanced specific surface area, because more number of molecules are exposed to the outer layer rather than using a spherical nanoparticle, and thus the performance is enhanced to much, because especially in nano scale, the specific surface area decides how much of matrix molecule will be in contact with the surface of the nanofiller, and that decides how much will be mechanical performance, what will be the interparticle distance, and then this interparticle distance decides what will be the complexity of the path required for a gas molecule from one side to the other side. If this path is more complex or more tortuous, then it will take hell a lot of time for a toxic gas molecule to pass from one side to other side, and that decides what will be permeability, and we can engineer this level of permeability by deciding what will be percentage and size of the nanoparticles. One important aspect of nanoparticle use in polymers is to have very uniform dispersion of particles. Otherwise, these particles have a lot of surface charge which is not balanced, especially because this is almost at the atomic and subatomic level. So a lot of electrons are free, and this decides the polarity of the particles, and they have a tendency to agglomerate, to attract each other, create clusters. If we do not agitate rigorously, nanoparticles will aggregate to create microstructures very quickly. That is why as soon as we create nanoparticles, they must be dispersed into some solvent. So it is necessary by ultrasonic technique for long period of time for the particles or the platelets to be dispersed, scattered uniformly, and then only we can achieve the performance. Otherwise, these clusters or agglomerations, points of agglomeration, they rather act as stress concentration points, and that can be region of deteriorated mechanical property. In some of our research, we have used nanoparticles for reinforcement of composites, along with fabric-based reinforcement, and substantial improvement of mechanical property up to 7-8% in modulus and thermomechanical properties has been observed. It is not simple to obtain nano dimension in particle. It is necessary to have prolonged period of grinding, So let me little bit go further. So in addition to mechanical property, we can have enhanced thermal, electrical, and other performance. Here is a demonstration of knife penetration resistance, which is like resistance to sharp objects, especially in stabbing or blast. When there is a blast, there are sharp nails of metal and glass. We come across this kind of explosion of bombs around the world. So if we have police force and military protected with some shields or vests with nanoparticle into the multiple layer structure, then the knife penetration resistance is improved. That has been already established by some research. So further, nanoporous structures are very aerosols are special nanoporous structures. They have very huge thermal insulation because they are about 99 and higher percentage of porosity. They have also a very high sound insulation performance because of this nano pore structure. However, thermal insulation is the result of enclosed or closed pores, and sound insulation is the result of open pores. Sound insulation, sound is wave. So the wave needs to be dissipated while passing through the nanoporous structure in textiles. Nanovents themselves are open porous structures. If we treat the nanovents with some aerosol or create the network of aerosol inside the nanovents, we have thermal insulation and sound insulation. Since time is short, I need to just touch upon such things, and such nano porous structures of aerosol are used for insulation of pipes and for insulation of human body, especially in space and high altitude. Nanotechnology, though so fascinating, it has some associated risk because the particles and the materials are very small in their dimension. They have every possibility to penetrate into human anatomy. They can be breathed, especially we are already using lots of nanoparticles in our cosmetics, dental, toothpaste, and cigarettes and vehicular smokes they generate. So we are inhaling. We are using a lot of nanoparticles onto our skin, and the pores in the skin also absorb some nanoparticles. Those who have been vaccinated with mRNA vaccines against COVID, they might know that the vaccine is based on nanolipids, and these nanoparticles of lipids are injected intramuscularly in our body so that they penetrate into the cells and they give the message to create antibodies, and thus the vaccine functions to protect us from the COVID. So you can see a very precise injection of nanoparticles into human cells can treat us against some virus, deadly virus. But at the same time, entry of some nanoparticle into our cells can also give a wrong message to develop something against human psychology, against human growth, and can create something like cancer. And it has been found through some research that the carbon-based nanoparticles and nanotubes are as toxic as asbestos. If they are inhaled into our lungs, they could create certain serious conditions. So for future, we need to very precisely understand the science behind such nanomaterials, how to convert such science into technology, and to find suitable applications so that the functions are regulated and we are able to encase on how we are using them. At the same time, we should not release extra nanomaterials into our natural resources because they are cause of concern for future. The complete life cycle has to be understood, starting from manufacturing to use and recycling. Otherwise, it could be another challenge for future, and we should not go into that situation. So here are a few books which have been focused to this field. I hope you are able to find it on the internet. I thank you for kind attention, and since time is little short, I need to stop here, and I'll be happy to address to any questions.
Thank you, sir. Participants have posted the questions. There is one question from one of the participants, Mr. Ravin. The question is, for light interference, which type of nanomaterial will be useful, sir? What is the idea of quantum dots, and how to ensure its deposition on textile and performance?
Yes, in fact, light interference is the result of a quantum phenomenon, and as is rightly pointed out, we need to decide which type of nanoparticle to be used. It is not with regular nanoparticles, but should be photosensitive nanoparticles. I think you can find it on in literature which kind of particles are photosensitive, and they must be in a regulated amount. It cannot be used in excess, otherwise overlapping of particles will not be able to create the interference what we desire. What is the second question? I think if you refer to the book which I mentioned, or you search about light sensitive nanoparticles, you will be able to find a lot of information in this area.
Okay, sir. So we'll take second question. Whether we will get silk fabric properties by the nanofiber finish extracted from silk fiber.
From silk fiber. Silk, what I mentioned is silk fibroin. Silk fibroin is some extract when silk is being extracted from the natural cocoon. So it is a waste material. When we produce fibers from waste, we cannot expect the same level of mechanical properties, but definitely, and what is very important, nanofibers are always too weak. Absolute mechanical property of nanofibers is very small. They cannot be used for creation of yarns and regular woven knitted fabrics. They are only functional material which is protected from both sides by sandwiching. The masks that we use for protection against virus is a multiple layer structure where the nanofiber is kept in the middle. Similarly, any kind of nanofiber, when it is coming into a mechanical action or action of wind, can be very easily broken and destroyed. So let us not expect the same level of mechanical property like in micron and higher dimensions, but functional properties are important. I do not say that nanofibers will replace the standard fibers, because such some properties cannot be achieved in nanoscale materials. Otherwise, waste material when converted to fiber also definitely are weaker, because the degree of polymerization is lower, and properties are critically dependent on such factors.
Okay, sir. Thank you so much, sir. Due to time constraint, remaining questions we will share it with speaker, and answers will be sent on registered email ID of the participants. So thank you so much, sir.
Thank you very much.
Yes, sir. Yes, sir.
Have a nice day.
Yes, sir. Thank you so much, sir, for such an informative presentations on nanotextiles. As a token of love and affection, we are presenting here with certificate of appreciation for your phenomenal and worthy presentation. Sir, kindly accept this appreciation, please.
Thank you. Thank you.
Thank you, sir. Now we will have next presentation by Dr. Ashok Rajpurohit. Dr. Rajpurohit is presently working as technical lead composites GE Renewable Energy LM Wind Power Bangalore, India. He has completed his graduation from DKTE, MTech from Indian Institute of Technology, New Delhi, and PhD from École des Mines, Paris Tech, Paris, France. Earlier, he has worked as project manager R&D in countries like France and Germany. He also worked as academic researcher at Karlsruhe Institute of Technology, Germany. He has published many research papers in national and international conferences. He is having proven expertise and skill sets in process and product development for structural, hybrid, and natural fiber composites. Such a renowned personality is going to present on topic fiber reinforced composites in wind turbine blades. We request Dr. Rajpurohit to start with his presentation. Please, sir.
Yeah. So you can hear me? Good. I'll try to share my screen right now.
Ashok, welcome you very much.
Thank you, sir.
Yeah. Please continue.
Okay, so if you can see my screen, I will try to put
Yes,
it in
sir.
presentation mode and continue with the presentation.
Visible.
Okay, so thank you very much for a very kind introduction, and good morning to you all who are part of this conference right now and listening to me. I welcome you all to this presentation and to this conference. I would also like to touch upon what Dr. Mishra just spoke about in the sustainability Venn diagram. Energy is the key parameter which requires attention when we talk about sustainability. And this presentation, where I talk about fiber reinforced composites that goes into wind turbine blades, I will also touch upon that energy puzzle of the whole sustainability issue. I was supposed to talk about a bit of introduction for people who would not know a bit of about me, but I think Professor Raibagi already did a great job in introducing me to you all. But what I would like to highlight here is what currently I'm doing and what I have been doing over the years. So in development and design of fiber reinforced composite materials, also called textile reinforced composite materials, that goes into applications ranging from automotive, aerospace, wind, and sports related application areas. I've been working with these high performance fibers, glass, carbon, and their hybrids into several of these applications, while certain projects that I did in Germany were also focused on application of natural fiber-based composites into automotive applications, specifically using jute, the Indian fiber, into a high-performance application or semi-performance application in the automotive door panels and other non-structural applications that Dr. Mishra also presented in one of his slides. So I call myself as a global citizen, as I've worked in multiple countries and multiple cultures. I have lived and worked there in Germany and France. I can speak English, French, German, and a couple of other languages, which is also one of my interests when I visit countries or work at different cultures. I have presented in multiple conferences, and what I proudly share is my experiences that I've gained over the years on participating in these top conferences on composite materials to witness what kind of work happens all over the world. Right now, when I'm associated with LM Wind Power or G Renewable Energy, the main focus of my work is on design and development of components that goes into or on the wind turbine blade, and also validation of those components structurally. The other responsibilities that I have here is to lead and manage a new technology development and production projects, and also work on failure mode and effect analysis for these new products or technologies from the process and design perspective. Having said that, I have a simple 4-point agenda for this presentation today. I like to talk about who are we and what do we do at LM Wind Power, what is renewable energy and how does wind play a role into renewable energy overview. I'll talk about wind turbine blade design and anatomy of wind turbine blades, and then in the end, talk about textiles that go into wind turbine blade production. So I start with my presentation with talking about the population that we have currently. So this is the current timestamp of population that you can all witness. And we are citizens of this beautiful place called planet Earth. It's a very nice place, but the climate is changing. And the decisions that we make today will define how our future is going to be. And population growth plays a very important role in making those decisions. As you know, energy consumption is increasing over the period of time, and there is a need for creativity and clever engineering so that we can find out alternate energy resources so that this planet can survive. As you know, in the Paris Climate Change Agreement, that 82% of the fossil fuel that we consume need to stay in the ground so as to achieve this 2 degrees Celsius limit that has been set by a group of 160 countries in the Paris Climate Agreement. And LM Wind Power, or what we do here, LM Wind Power, is the center of what the requirement is. We have clearly defined vision and mission to achieve this, and that is a clean business and a clean planet. What we do here to achieve this clean business and clean planet strategy is we work with our customers, with our suppliers, with the employees, with the government agencies, and also with our competitors so as to achieve a development and a progress which is good for our environment and also sustain and adds to the sustainability part of this whole puzzle. We are the largest supplier of the independent supplier of the rotor wind turbine blades to the world industry. So right now, if you imagine the number of wind turbine blades that are running onshore, offshore, anywhere in the world, 1/5 of all those wind turbines would have passed our world. So that defines how large are we and how are we contributing to this sustainability and renewable energy puzzle that the world is facing in terms of its challenges. What speciality we have when we say that we are present all over the world is we are present close where there is a requirement. So we are close to where the wind energy is required, where the wind blades are assembled, and this helps us to minimize the risk, to efficiently deliver transport and logistic solutions for these wind turbine blades, and also enable us in some way to use the local materials into a global process stream. That brings us to what are we and where we been. So we have a headquarters here in Kolding. Since 1978, we produced wind turbine blades in Denmark. And over the years, we have expanded into multiple continents and multiple countries, including in Brazil, Canada, China, India, Poland, and all over the globe. And a snapshot of the heights of our presence all over the world. This is that I showed you in the dotted map in the previous slide. And we have about 14,000 people working for producing the blades, designing the blades, delivering the blades to the right customers and solutions. We have produced so far since 1978 about 240,000 blades. As I say, this is about 1/5 of the blade that are currently these 241,000 blades, or about 13,000 blades that we produced last year. We have an installed capacity right now of about 121 gigawatts. I just have a question. Do you hear me clearly right now? Can someone just?
Yeah, you are audible. You are audible. Continue.
Okay. Yeah, I saw that probably my internet connectivity is poor, so I wanted to just confirm. So basically, this 121 gigawatt of capacity of energy that we produce using LM wind power blades contributes to about mitigation of about 251 million metric tons of carbon dioxide that would have been emitted by using any other source of energy. So we have a huge impact on the world in terms of what we do and how we do it. We have a long history also. While I have been talking about 1978 when we started producing blades, but I'll not go into details the slides about our history, but there are two that I would like to highlight in our history. One is our origin. So we started as a furniture manufacturer around the World War II period, and then transitioned into manufacturing of glass fibers in the name of LM glass fibers. And these glass fibers were further used into applications such as furnitures or into these camping trucks and into shipbuilding and stuff. And at some point, we wanted to use these fibers also into wind blades, and that led us to start with the production of wind blades about in 1978. And since then, we have been producing blades which are longer and growing and being delivered all around the globe. So that is one part of our history. The other part is how India has been a significant partner in LM's growth journey. So India was the first country where LM produced blades outside Denmark. And that was about in 1993. And since then, we have 3 factories here in India, a technology center in India that caters to the whole world market. And right now in 2017-18, LM Wind Power is acquired by GE Renewable Energy. So we are part of the whole GE business, specifically focusing on renewable energy and delivering not only wind blade solutions, but the whole wind power blade generator tower assembly solutions to the renewable energy market. So that completes the first part of my agenda point, and we go into the second one where we talk about how does the renewable energy come from, or where does all the energy come from. So as you might know, sun is the source of energy, and it's the ultimate source of energy. The light from sun Yeah, let me have a laser pointer. So the light from sun gets converted, gets used by plants and animals to have food, and then heat, pressure, environmental conditions, and time, a long time helps us create these fossil fuels or non-renewable energy in the form of coal, oil, or natural gas. While this light and heat that comes from sun also enables to heat up the land, it enables our rain cycle, it creates vortexes, and that allows us to harness the wind and the solar energy that comes from wind. And these energies that I talk here in the bottom column are form of renewable energy that has a source in sun. And just for context, sun delivers about 1.74 into 10 raised to 14 kilowatt hours of energy to Earth every hour. And from this whole energy, only about 1% or 1 to 2% of energy gets converted in the form of biomass for animals or wind for the Earth. And what amount of energy that we harvest from these 1 to 2% is very, very, very negligible. So there is a huge scope where we can work on this. What kind of current energy source we are experiencing? So this is the data from International Energy Agency, which monitors the energy data from all over the world, including the nuclear data. And what we see here is currently more than 60% of energy that we use comes from coal, oil, or gas, which are all non-renewable energy sources. While wind and solar have a certain sizable portion, but it is just 6 or about 6% for wind energy. And there is a huge scope that we see in terms of wind, solar, or other renewable energy sources taking out or eating from the pie chart that exists for gas, coal, or oil-based energy sources. An interesting data point that I found on IEA is about the amount of energy that we add year on year in terms of the world energy capacity. And if we see just for the renewable energy, you see that from 2019 2020, we have about 45% increase into the amount of energy we produced using renewable energy sources. And this increase is even higher when we just consider the data point for wind energy. For example, from 2019, if we added about 60 gigawatts of wind energy, we have added more than 130 gigawatts, that is more than 90% than what we had added in 2019. So I think we as a world are on a right track to harness these renewable energy sources, and not only to harness them to an acceptable level, but to a level that we cannot imagine right now. So that has been the growth journey for wind energy so far. This brings us to what we have been doing and what we are. So right now, the wind turbine blades are getting bigger and bigger, and that is part of our agenda at LM Wind Power and also all over the world. So about in 1998, it was established that 23.5 meters of a turbine blade would be a maximum, which would achieve the maximum efficiency and could sustain for a 20-year lifetime. But that myth has been broken not only by LM Wind Power over the years, but all the wind turbine blade manufacturers. And right now, LM and GE holds a world record of producing the longest wind turbine blade that have been established for offshore wind energy production. And the length of this blade is about 107 meters with a rotor diameter in total of 220 meters. If you compare this, it is close to what an Eiffel Tower or a Statue of Liberty would look like from far away, but this blade would even shadow those other monuments that you see as the wonders of the world. What other things that I would like to highlight here is the way an anecdote that is what I heard from a publication, and it talked about comparison of wind energy production with a comparison of agriculture. So a farmer, the produce of agriculture is defined from the amount of area that he cultivates to produce those agricultural crops. Similarly, in wind energy, the area that is swept by the tower defines what amount of energy are we consuming. So this is like farming of wind, but in a vertical plane. And that is something that the wind industry is currently looking for. And 107, though, might be a very optimistic target right now, but I think based on the technologies we are trying to also improve upon them. And to cover this journey from 7 meters to 107 meters, key was the technology. And LM has been developing innovative technologies to develop these wind turbine blades that would be used for future and to sustain sustain the energy production that the world currently requires. So what are the rotor blades? And you have seen, how we come from renewable energy to wind production. And I would like to talk about why rotor blades are the critical components in the whole wind energy production chain. But before that, let me take you to a components of a wind turbine blade. We have three important components. As you see, we have a tower, a nacelle, and the rotor blades, which consist of blades plus the central rotor. While the blades and the rotor are purely a composite material part, the tower and the nacelle are not generally composite structural parts, but they could be metals. And the important aspects of this control system are the two important points of yaw control, that is controlling the direction in the wind direction in which the wind blows. The yaw control moves the face of the rotor in that direction, while the pitch control changes the angle of attack for the air on the blade so that we have maximum efficiency of energy extraction from the incoming wind blade. Now, why I say rotor is the motor is because of certain points that I show in this slide. And this is not only the focus of what I do at LM Wind Power, but what LM Wind Power itself does. And the rotor blades alone represent about 15 to 20% of all the investment that goes into a wind turbine manufacturing. And rotor blades, or for example, to say improving the efficiency of wind production and reducing the cost of wind energy generation. And the most direct way to achieve those two objectives is by improving upon the wind blade and the rotor. And if an increase in about 4 to 5% of AEP, that is annual energy production from the wind turbine blades, happens by optimizing the rotor itself, then the cost of the whole wind turbine blade set is just covered by its lifespan of about 20 years. So that is an interesting anecdote also in terms of why rotor is the motor and why a special focus is provided by researchers at our company and also all around the globe to improve how efficiently can we manufacture these rotors. And as I said, reducing cost of energy is the key. And there are three aspects into which these costs of energy can be reduced. And this happens at LM Wind Power and GE in general. The first one is we improve the blade design. So we increase the rotor size, we add modularity or flexibility to the wind turbine blades that they can be interchangeably used into alternate hubs or alternate blade platforms. And we customize by adding of added components on the blade surface, for example, T-spoilers or serrations that you might have heard. This helps us improve the energy or annual energy production. And so we reduce the cost by clever designing. Further, the cost reduction can be majorly also improved by using efficient materials. Glass fiber materials and polyester is a proven technology, but there is always scope of improvement in type of material that we use and the sources from where we can use those materials. You develop hybrids and a different kind of liquid polymer systems along with styrene gel coats also help us enable reducing the cost of energy through efficient materials. And finally, the processes. While we have been producing blades through vacuum assisted resin infusion process over a long time, but there is always scope of improvement. So we use Six Sigma lean manufacturing technologies to identify where are the process related points that we can improve. And because of our presence all over the world, we are able to also improve upon process. We have a quick changeover time and we can deliver blades fairly quickly. So we use this industrialization and production at a mass scale to our benefits to deliver the cost, to deliver energy, reduce cost and highest efficiency. So this brings us to the final two sections of my presentation, and that is on blade design and anatomy of the blade. So in the figure on the left, what you see is the isometric view of how a wind turbine blade looks. on the left, we have the root, which is circular to be mounted on the hub. And on the right, we have the tip of the blade. And there is a transition zone where the circular root is converted to an aerodynamic profile that you see on the bottom of this figure. Why this aerodynamic profile is important is because this aerodynamic shape or profile decides how much of energy that is incoming from the speed of the wind is converted into, for example, electrical energy at the end at the end of the wind energy production. There are a couple of important terminologies that I would like to highlight here. Pressure side and suction side of the wind turbine blades are, the upwind and downwind side where the wind passes. And for example, when the wind passes on the upwind side, it forces the wind turbine blade because of its aerodynamic shape. It forces the wind turbine blade to move up, and that causes the rotation motion to the wind turbine blade. Then we have the leading edge side and the trailing edge side of the wind turbine blade, where leading edge generally represent the incoming air. So the air that attacks the wind turbine, it attacks on the leading edge. And you can imagine if the blade is attacked by on the leading edge by wind which is blowing more than 100 kilometers per hour, how can it sustain erosion and also erosion due to rain for about 20 years? So this is one of the critical components of the wind turbine blades also. And then we have the central components here. We call them shear webs and spar caps. And spar caps are running on the center of the two shells. And these are the main load carrying member of the wind turbine blades. What I mean to say here is that the whole cross section or profile of a wind turbine blade depends on what kind of loads it is going to experience over its 20 to 25 years of lifetime based on where it is installed. And without going into much details about what kind of loads this wind turbine blades faces over its lifetime, there are two important forces that acts over its lifetime, and that is a flap-wise fatigue force and an edge-wise fatigue force. When I say flap-wise, it's the wind load. So the wind blowing onto the blades bends the blade along its length, and that happens every time a rotation happens. And this is what it has to sustain over its lifetime. And the other is the edge-wise load. So edge-wise load is, if you consider this leading edge and that as trailing edge, then there is always a fatigue loading on the edge-wise direction for the blade when it's rotating due to its own weight. And these two are the main loads that the wind turbine blade has to sustain all on its own lifetime. And there are a lot of established design parameters. So strength of the whole laminate, because I say laminate because this wind turbine blade is basically a composite laminates. So strength of laminate, strength of the bond at the leading edge and trailing edge. Why I say bonds, I'll show you in the next slide. Strength of the root solution, because if the length of the blade increase, the weight of the blade increase, all of them has to be sustained into the root section also. As blade stability, tip deflection, eigenfrequencies of the blade and resonance, all those decide what would be the cross section of the blade and what kind of loads it will be able to sustain. Quickly moving to blade manufacturing, you might probably know that all the composite material parts that are longer than about 1.5 or 3 meters would be produced by a very standard process called vacuum assisted resin infusion process. And specifically for a wind turbine blade, we have two of these processes established. So we have one mold for the downwind, so 1/2 shell of the mold, and the other mold for upwind. And what we do is we prepare the mold by applying release agent and all the necessary preparation. We lay up dry fiber glass materials, so glass because glass is most widely used, but other fiber materials into the blade cross section, ensure its strippability to the cross sectional shape, and then cover it by vacuum foil, seal it from all the sides, and apply a vacuum pressure of about 1 bar, and then inject resin through resin injection machines and the pipes, and also the vacuum enables the resin injection machine to put out resin into the blade cross section. Once this part is cured based on what kind of resin system is used, we add the shear webs that I showed you in the last slide as a stiffening element, and then close the other half mold on the top of it, apply a structural glue on the periphery of the first mold and the second mold, and that in the end, when you demold everything, you have a wind turbine blade that is ready to be going into finishing and being assembled onto a wind turbine. So what kind of material or major materials that goes into the wind turbine blade manufacturing are the reinforcement that I talked here. So glass, carbon, and other allied reinforcements are the major materials. Then we have core, that is balsa or polyester to add to the stiffness of the composite materials by adding sandwich materials. And then we have resin, of course, and the adhesive that is used to glue the two half shells together. But there are other indirect materials also in the form of infusion consumables that comes in the part 3 of this process chain, where we have fish nets, we have infusion pipes, we have peel plies and other materials that I'll talk about in one slide. Why or how does this blade anatomy decide what kind of reinforcement go into the wind blade manufacturing? So in this exploded view, you see gray areas. These are the areas which experience the maximum load while the wind blade is in operation and also during its transport. And these areas generally that you see here in gray are covered by unidirectional reinforcements in the form of structural reinforcements. And as you know, composites are the materials whose mechanical behavior depend on the orientation of the fibers present in those composite materials. So orientation of these high performing areas is unidirectional reinforcements, while we have other areas, for example, root or the whole surface of the blade, which is covered by bidirectional, or we call it BIX, or tridirectional or triax materials, so as to ensure not only the tensile properties, but also shear loading conditions that is maximum influenced by the other blade areas here. As I said, core materials are part here in some areas because to avoid the buckling load that occurs onto the wind turbine blades. Imagine if you have a straw and if you're trying to bend a straw, it will bend to a certain extent, but after a certain extent, it will create a kink and it will just, have a kink in the end, and you could easily fold the straw together. And for that, we have the third section that is called shear web, which basically comes at the center to avoid the buckling of the whole aerodynamic profile also. And there could be 1, 2, or 3 shear webs. And the shear webs, because it is majorly experiencing a shear loading, it will have biax reinforcements in this shear loaded region. This brings us to the final section. I hope I am in time. I want to also let time for a couple of questions. So let me quickly drag you through what kind of fibers and textiles goes into wind turbine blade. Most of you know glass fiber is the major material that goes into wind turbine blades, and this is not only very recent, but since a couple of decades. And utilizing glass fibers, we at LM have been able to reduce the energy production cost for about 10% for at least 3 decades. And right now, cost is an important factor, but there is also an important factor of how efficiently are we reducing this cost and producing energy. And that brings us to other kind of materials. So why we use glass fibers is because of its stiffness and its lightweight compared to metals. But then we have new generation of glass fibers in the form of S glass or S2 glass. S basically goes into aerospace or high performance applications, while S2 glass is also a high strength, high modulus glass that can be used and have been used into wind energy for certain applications, though the cost of S2 glass or high strength glass is about 10 times higher than what we have for E glass. The other non-glass alternative, which is very prominently used into wind turbine blades, is carbon fiber. Now you know that carbon fibers are costly, but it is also stiffer, it is stronger, and it is lighter in weight and lighter in density compared to glass fibers. And so as we are aiming to produce longer blades with higher energy efficiency, we would like to also explore about carbon fibers. And there have been already developments into not fully manufacturing a commercial wind turbine blade by carbon fiber, but there are already efforts happening on even LM wind power. When I say we produce the longest wind turbine blade, that would not have been possible without inclusion of glass fibers into the main structural element. If you remember, I called spar caps the main structural element, were made from spar caps for those 107 blades. Other non-carbon, non-glass alternatives are aramid, which is not very widely used for longer wind turbine blades, just because it doesn't have a good compression behavior, and it is also not very compatible to majority of the resin systems that we currently use, both polyester and epoxies into wind turbine blades. But one other interesting alternative that we have is in the form of basalt fibers. You know, basalt is a renewable fiber. It is naturally occurring mineral fiber or rock fiber, and it has a strength which is 30% strength and stiffness which is 30 and 15% higher than glass fiber, and it is also lighter, about 15% compared to glass fiber. So that has also been used into some commercial application, but the only limitation is how we can get a supply chain which continuously supplies basalt fibers for wind energy production. Coming to the reinforcements, as I have already talked about, in spar caps, we have unidirectional reinforcements, and there are major players in the form of Owens Corning, Shomara, SGL, Sartex that are also present in India that supplies these unidirectional reinforcements, both carbon and glass, for the spar cap application. And this unidirectional reinforcement is manufactured using technologies such as LIBA or Carmeyer's multi-axial weaving or multi-axial knitting technologies. While the shell area, the root area where we require the maximum reinforcements, and the shear web area, we have not unidirectional reinforcements with bidirectional or tridirectional reinforcement that you see in the figures attached. And these reinforcements are also manufactured on multi-axial technology. While we speak of biax, we already know that we want fibers into two directions, but that is not possible because of woven fabrics or other woven fabrics with different type of weaves is not suitable for composite manufacture, just because of crimp, which is a determinant factor for composite materials. Two important things that I highlight in this slide is the kind or the way forward that happens in the reinforcement technology. One is development of carbon glass or carbon basalt or other fiber hybrid alternatives, so that we reduce the cost, we keep the cost in control, we keep the weight in control, and we improve the efficiency of not only the production, but also the energy production. And the other one is in the form of using preform. So preforming is an intermediate step when we manufacture the composite materials. And this intermediate step is basically combining all the layers that we generally would have laid into the mold while producing the blades, making a preform assembly outside the mold, and then directly delivering it to the mold surface. And then just before injection, that reduces the cycle time and adds to the efficiency of production. And in non-structural consumables that I talked about in the form of chopped strand mats, polyester wheel that goes onto the surface of the blade to improve the evenness, to apply the gel coat that can help the blade sustain a longer lifetime. And then we have certain flow assistant fabrics. These are glass fiber or polyester fiber based fabrics that enable flow into the reinforcement during vacuum infusion process. And these are not only structural, but they aid the infusion process itself so as to produce a defect-free composite part in the form of a wind turbine blade. There are other materials such as nylon ply or breather fabrics that is also made from polyester or nylon, and these are also used as part of infusion consumables to manufacture these wind turbines. There are a lot of scope which a textile engineer can help develop and optimize wind energy production using the wind turbine blade optimization. Now they bring me to again the point where I started about population growth. So if you look at the population growth right now, what you'll find is we have about 1.14% population increase in this world every year. That means we have about 80 million or 8 crore people added to this planet every single year. And that brings us to think, if we are going to reduce, or there is no chance an individual will start consuming less energy than it used to consume yesterday. So wind is part of this answer to this problem. And that is why LM Wind Power has a commitment to capture the wind and to power a cleaner world through efficiently delivering wind turbine blades at different locations in the world. This brings me to the end of my presentation. I would like to thank you, each one of you, for your attention. And if I have not overcrossed the time, I would like to also accept questions that you may have for this presentation. Thank you.
Excellent presentation, Dr. Ashok Rajpurohit. Thank you so much. There are questions. One of the question is by Professor Nico. The question is, do you also use resins with a dicyclopentadiene instead of styrene? The question is, yes.
It's okay. Yeah. So I think right now commercial blades are mostly using styrene-based resin systems, and this is somehow also different for LM Wind Power, because LM is like only few players which uses polyester resin, while all others uses epoxy-based resins, which are even stronger than polyester resin. But efforts are going on everywhere. And right now, if you might have heard about helium, or there are certain resin systems from Aditya Birla, which also has a recyclable component into it. So efforts are going on. There are certain things that we also try to do. But yes, but right now the answer is probably no.
Okay. The other question by Mr. Atik Sheikh is, he said, nice presentation. Can you share what will be the lifespan of blades in different climatic conditions and extreme climate, and what can be done to improve the same? This is a question.
Yeah. So since the blades have been started producing in 70s, 80s, the lifetime of a blade is assumed to be about 20 years. And the only good thing earlier was that a manufacturer would just deliver a blade, and then the maintenance of the blade would be someone else doing it. But right now, that is not the case. The one who manufactures the blade also ensures that the lifetime of the blade is 25 years. And that is also a struggle that, or a challenge that the wind blade manufacturers are facing. And it is not at all worked on. So there are all the climatic tests that happen onto the wind turbine blades happen on one of the test blade that is designed and produced. And right now, for example, we are also working on a technology that can be used into an extreme cold climate condition. So the wind blade that goes into high mountains, into snowy areas where there is snow for about 6 months a year, we try to also optimize the blade conditions, its surfaces, and the way into which it will produce energy so that it can sustain its lifetime and deliver to the commitment made in terms of the amount of electricity it will be able to produce. So that is something that is also on focus for all the blade manufacturers.
Thank you. Similarly, due to the time constraint, we will post the questions through mail, and answers will be sent on registered email ID. Now, I once again I will share the screen. If you stop the sharing the screen, sir.
I should stop. Okay, here.
Yes.
Thank you. Thank you very much.
Thank you. Thank you so much once again, Dr. Rajpurohit, for such a noteworthy presentation. As a token of love and affection, we are presenting here with certificate of appreciation. We request to kindly accept this appreciation, please. Thank you. Now we will go ahead with the next presentation.
Today's third technical presentation is by Professor Dr. Nico Behrendt. Professor Nico Behrendt is working as professor at Hawk University of Applied Sciences in Chemical and Process Engineering in the field of textiles, materials, and environmental technology. He is also the head of the bachelor's program Innovative Textiles and honorary chairman of the association Circle of Friends for the Internationalization of the Textile Competence Center, Munchburg at Hofstra University of Applied Sciences. He is doctorate in engineering with the topic development of new cellular polymer electrodes through targeted morphology control. He has specialization in the area of polymer chemistry. Earlier, he has worked as a development engineer at an automotive supplier. He also has worked with Volkswagen Group of Research. He has a very diverse experience in the field of materials research. Such a stimulating personality is going to give presentation on new approaches to the production, chemical modification, and use of smart nanofibers. We request sir to start with his presentation. Please, sir. Please share your presentation, sir.
So, okay. Thank you very much, Ms. Shaban, for this kind introduction. At first, my question, can you see my slides?
Yes, sir.
Is it visible? Okay. Yeah, thank you very much. So, okay. Yeah, thank you very much for this kind introduction and for this great opportunity to give a presentation here in the frame of the ITPP 21. It's my first time here, yeah. And when I read the program, I saw that we have a lot of nanotechnology experts here in our conference. And therefore, if I switch to my overview, maybe for the experts, the first two chapters with fundamentals and production processes and influencing parameters are a little bit boring. However, it is important to understand the last very interesting chapter with the new approaches. And yeah, in the morning we have heard something from Professor Mishra regarding nanofibers and nanotechnology. Therefore, I will pick up some of the issues. Yeah, at first I will start with the classification of nanofibers, and then I was a long time a leading development engineer in the filtration industry, in the automotive industry. Therefore, I will explain you in short some aspects regarding the filtration. Then I will go on with the production processes and the influencing parameters. Yeah, I will explain a little bit to the topic lab scale arrangement for the production of nanofibers. And I will give you an overview regarding the influencing factors of the concentration of the spinning solution and of the voltage and so on. And then I have also a picture but we have seen it also from Professor Mishra. I have also a picture from this Elmarco company, because I had in my former time in the filtration industry, I had a strong cooperation with the Elmarco company, and therefore I will explain it also a little bit in detail. And yeah, my last chapter are the new approaches. At first, maybe you know, nanofibers are very, very small, and therefore nanofibers are also very sensitive against mechanical stress. Therefore, I will show you an approach to improve the mechanical properties, the mechanical resistance of the nanofibers. And last but not least, I have an approach, nanofibers with PTFE particles. Maybe your first question is, especially of the experts, what should be the reason why we should use nanofibers, or why we should produce nanofibers with PTFE particles? And therefore, please stay patient. I will explain it in one of my last slides. And therefore, it should be also very interesting for the experts, I think. So, okay, let me start. Here you can see a short overview regarding different sizes, regarding different materials. You see in human hair, you see the cellulose fibers often used in the filtration industry for the air, for the gas filtration, for the oil filtration. You see that are typical diameters of 20 microns or 15 microns. And then we have some synthetic fibers in the range of let me say, of the so-called sub-micro range. That means roughly 1 or 5 micrometers. And you see also the spider web. Yeah, also in the spider web, we have very, very small fibers, small in diameter. And here you see that are nanofibers. There's no clear definition. Yeah, there's no common clear definition for nanofibers. I know some companies, they produce fibers in the range of 500 or 800 nanometers. And they say also, or they call their fiber also nanofibers. But let me say, in the real sense, you can say nanofibers are fibers with a diameter of 100 nanometers. It's also possible to produce fibers with 50 nanometers. Yeah, that's also possible. However, it's not so easy to produce nanofibers with 1 or 2 nanometers, especially in the industrial scale. Okay, look at these pictures. Look at these pictures. You see here the comparison of a conventional filter media without any nanofibers. And here there is a scanning electron microscope image with a conventional media coated with nanofibers. And I'm every time really impressed by these pictures because what you can see here is the typical effect. Yeah? These filter media were stored for several weeks in a highway tunnel, yeah, to filter all the fine dust, to filter all the soot, yeah, from the combustion engines. And you can see, yeah, that the filter media with this nanofiber coating is much more efficient, yeah, in comparison to the conventional filter media, because what you can see here is all the nanofibers are surrounded with the fine dust particles. Yeah? That means in the case of the nanofibers, we have a really good dust collection, yeah, because of the really large surface, yeah, and therefore it makes sense to work with nanofibers, especially for the air filtration. Now you can say, okay, in the future we have more electrical cars, yeah, like this battery electrical vehicles. We have not so much combustion engines. However, please keep in mind, we have also particles as tire wheel particles, and we have also dust from the brakes and so on. And you know, all this fine dust, there's a lot of this, there are a lot of discussions here in Europe are very harmful for the human health, and therefore it's really important to remove all this fine dust materials through the filtration, and therefore to remove all this fine dust particles from the humans, yeah, and therefore such nanofiber coated materials were also used, for instance, for the cabin air filtration. Okay, that's one effect. Let me explain you only some basics regarding the filtration, yeah? And how we can measure the efficiency of a filter element, how we can characterize the filter element. At first, you see here the typical measurement. Yeah? We have here the crude air side, yeah, with, let me say, the dirt, with dust particles. Yeah? And then here we have a filter element. And after the filtration, we can see that we have a diminished number here of dust particles. Yeah? And here we have the first parameter, very important for the filtration. Yeah? That's the so-called filtration efficiency. That's the collection efficiency. And in my opinion, it's really clear. Yeah? If you have 100 particles here on this side, and after the filtration, only 10 particles here on this side, then you have a filtration efficiency of 90%, of course. Yeah, that's easy to understand how we measure it. We use a so-called particle counter. That means you can use the light scattering of the particles, or you can use so-called dark field methods. That means you measure the shadow of each particle, and therefore it's also possible to count the particles. Okay. However, the collection efficiency is one important parameter. Another really important parameter is the so-called pressure drop. Yeah? That means we have a certain airstream velocity. Yeah? We use 300 to 600 cubic meters per hour. Yeah. And believe me, it's really, really easy, yeah, to construct a filter element with a collection efficiency of 99%. You can use some tissues for it. Yeah. But on the other side, it's very important to have a really, really low air resistance. And that's not so easy, yeah, to create a filter element with a high collection efficiency next to a low air resistance. And one important value for the measurement or to get an idea regarding the air resistance is a so-called pressure drop. Here on the crude air side, you have a certain pressure, yeah, and of course, due to the air resistance of the filter element, you have a certain drop of the pressure. That means the pressure here is lower than here, and the typical value, what you measure or what you give, is the so-called pressure drop. Yeah. Okay, there are also some other important parameters, clogging and so on, clogging time, but I cannot explain it here in the frame of this presentation. So let us go on. And here, let me say that's an easy lab scale trial, what you can see. Let me say it's really easy and it is used in the lab, but only, let me say, for show purposes, because you can see here you have the inject, the syringe, with a certain amount of solution liquid. It's a polymer solved in a solvent. Then you have a needle, yeah, and here you create a drop. And next to this, you have applied voltage, which is here applied, and here there is a grounded plate. Yeah, we have opposed polarities between here and here. Yeah, and in this lab scale arrangement, we form a drop here. Yeah, and maybe you know it from the water tap. Yeah, there are several fluctuations in the drop from long to wide, from wide to long, and by the fluctuations, and we have a certain movement, and next to this we inject charges, yeah, charge carriers by the applied voltage. Yeah, that means we have a really, really high charge carrier concentration into the drop. And now we have the following effect, that the system try to dilute the charge carrier concentration. And how we can do this? Yeah, we can do this if we form a jet, yeah, which tends to this side or to this side. Yeah, and then of course, if we have the creation of this jet, maybe in this side, we have also the agency of this grounded plate, of this ground plate here, of the other electrode, you can say, with the opposed charge polarity. That means we have an inversion of the direction, yeah, maybe to here. And then again, we have an inversion of the direction too, yeah, and the whole process is called whipping or inflammation. That means this effect, yeah, let me say, especially this dilution of the electrical charge carriers leads to the effect that we have a stretching of a jet, of a pre-fiber, and next to this we have evaporation of the solvent, and therefore, yeah, we have the formation of the nanofibers. Yeah. So, and let me say, so the dilution of this charge carrier concentration, yeah, because you know, if you have this uniform charge carriers, you have a strong repulsion, yeah, between all the charge carriers, and therefore, of course, you have yeah, this jet formation to this side or to this side. Yeah? Okay, so this idea, yeah, is very, very old. It was invented by Anton Formhals in 1934, yeah, and he also applied several patents, and also he described, let me say, yeah, the first industrial scale, yeah, for the production of nanofibers, and it was also mentioned by Professor Mishra Here you can see this rotating cylinder with these spikes. Yeah, spikes are very famous at the moment, but in another context. Yeah, or you can also say teeth. Yeah, it's like a gear wheel, and you see that this gear wheel is rotating. Yeah, in the spinning solution. Yeah, we have also in applied voltage, and therefore, let me say from the spikes. Yeah, we have a certain excess voltage, and therefore we can use it as a spinning unit, yeah, in the industrial scale, because if you use such a rotating cylinder, it's much more efficient, yeah, much more efficient than this the syringe, what you have seen in the lab scale equipment. Yeah, okay. Therefore, it means it was invented by Anton Formhals, yeah, in earlier times, and now we have to clarify a little bit. Yeah, what are the effects? And okay, in the most cases, the aim is to create really, really thin nanofibers, 50 nanometers or maybe less than 50 nanometers. And you can see the influence of the different parameters. At first, of course, if you have a high concentration of polymer in a polymer spinning solution, of course, you have increase of the fiber diameter. The same effect we observe with the flow rate. Yeah? Let me say, if you have a high flow rate, you create bigger drops or droplets, and therefore also higher fiber diameters. And then we have also the effect of the electrical potential. The electrical potential is the voltage divided by a certain distance, between the electrodes. And if you have a high electrical potential, you have a high inducement of the droplet to start the jet, of course, and therefore it's so if you have a high electrical potential, of course, you have a low fiber diameter. And the same is with the electrode distance. The electrode distance in the case of a constant electrical potential, that means if you increase the electrode distance, that you also increase or that you adapt the voltage, of course. That means in this case you have also a decrease of the fiber diameter, because you can say it, you can see it in that way, that you have more space for the whipping process. Okay, that are the influences, and now you see this. You will know this picture from the presentation of or this picture here, the small picture here on the side from the presentation of Professor Mishra. This is a pilot line from Elmarco, what you can also use for an industrial scale. And also, only to give you a little bit more understanding in this direction, you can see it here. We have 2 spinning units, and in every spinning unit we have 4 of these spinning cylinders. And here we have our substrate. You can recognize it. That means the substrate is coming from this side. And then here we have the coating process with our rotating cylinders, to ensure an uniform coating with nanofibers. The electrodes are a little bit displaced to each other. That's also very important. And here you can see also some typical spinning solutions. For instance, polyamide 6 is often used, solved in formic acid or solved in a mixture of formic acid and acetic acid. And also polystyrene is possible to use or can applied from a solution in methylethyl And that is a typical, let me say, more or less industrial scale. It's a small industrial scale plant for the coating of substrates of nonwovens or cellulose materials with nanofibers. And here I forget what is the function of this part of the machine. Here are the tanks for the spinning solutions. It's stored here under the spinning units. Okay, and only for you to give to have an impression about the industrial scale. Today there are a lot of other lines which are much more bigger, which have a higher productivity, of course, but you have seen it also in the presentation of Professor Mishra. Therefore, I will go on with my filtration. And now it's a question how we process the filter media. Yeah? You have seen here in that picture that we have a non-woven, yeah, for instance, or a cellulose material. Yeah? And that's a base, that's a substrate. Then we carry out our nanofiber coating with the electrospinning process. And then we have a really bad process. It's a so-called pleating process. That means we form folds in the filter media, yeah, to increase the surface for the filtration, to make the filtration more efficient. And last but not least, we have the filter element. Okay. Therefore, my first approach is the elastic modification of nanofibers. Now it's interesting for the experts. Yeah, that means during the pleating process, yeah, if we create our folds, we have a high level of mechanical stress for the nanofibers, and therefore we can improve it if we modify our nanofibers, if we do or if we carry out an elastic modification of the nanofibers. And therefore I developed a method, yeah, to increase the mechanical resistance of nanofiber webs by the implementation of thermoplastic elastomer domains or thermoplastic elastomer particles. What that means, here you can see an SEM image, yeah, scanning electron microscopy image, and you see the nanofiber network, and here are the TPE domains implemented. In this concrete case, I have used TPUs, yeah, thermoplastic polyurethanes. You see these materials are commercially available, yeah, and I have implemented these domains here, and the effect is, yeah, these domains act like a mechanical spring, yeah, like, let me say, it helps to endure mechanical stresses because with this implemented domains, there is an elongation of the network possible without the destruction of the network. Yeah, and therefore it helps, or the implementation of the domains is very useful, is very meaningful for the network to suffer all this mechanical stress during the pleating process. And to give you some values, and also to explain why I have explained also these different filtration parameters. Here you can see the effect of this TPE domains. Yeah? If you compare a standard nanofiber coated material without any TPE domains, yeah, you see you have a certain value of the collection efficiency. However, if you implement these TPUs, yeah, during the spinning process, yeah, you have a higher collection efficiency, yeah, of roughly 10–15%. Yeah, you can see it here, and that's the effect of this TPE domains, because you can say in this case we have not so much destruction of the nanofiber network during the pleating process, and therefore we can survive, you can say, more of the nanofibers during the pleating process. Okay. And therefore we have also a higher collection efficiency. Yeah, and you see also you have learned collection efficiency is one thing, but another thing is the pressure drops, the air resistance. And here you can see a comparison, and you see the comparison of the modified and the standard material. There is no big difference. It seems to be that the modified material is a little bit better, yeah, because the pressure drop is lower. Yeah. However, it's in the frame of the measurement error, and therefore I would say it's nearly the same. So that's one approach. And let me say, okay, why it's important to compare all these parameters, or why we use nanofibers in general in the filtration. The effect is that we have a really high collection efficiency, because we have a lot of space for the dust collection. You have seen it in the first pictures. And next to this, we have a certain effect called slip flow effect. That means, nanofibers are so small that we have, in the ideal case, no laminar layer surrounding the nanofiber, because you have to know that a laminar layer has a flow velocity of 0. And if you have this laminar layer, you have a higher air resistance. And in the ideal case, at least in the ideal case, that means that if you have no laminar layer, you have, in the ideal case, a really, really low air resistance. And that's the effect, or that's the purpose why the people use these nanofiber networks, especially for the filtration. At first, dust collection, high collection efficiency. And the second one is, if we coat a material with this nanofiber network, we have only a really, really low increase in the pressure drop. We have only a little bit increase in the pressure drop, in the air resistance. Okay, that's the first approach. And now the second approach, nanofibers and PTFE particles. Why we should use PTFE particles in the nanofiber networks. PTFE has, or every material scientist know that PTFE, Teflon, in the common name, has some really outstanding properties. A lot of outstanding properties, and one of the outstanding properties is also, or are also, the so-called charge storage properties or electrode properties. That means PTFE is able to store and to stabilize electrical charge carriers in a very efficient way. And therefore, it makes sense to implement some PTFE particles in the nanofiber networks. Because, as you already know, if you have dust particles in the air, there is a certain friction between the dust particles and the air, and therefore you have a so-called effect of triboelectricity. That means it is an electrical charging process by the friction between the air and the dust particles. And therefore, you can say a lot of particles in the air are charged with electrical charges. And if you have also charges on the PTFE particles, then you have attraction between opposed charges, of course. And therefore, if you implement these PTFE particles in the nanofiber network, you have a higher chance, or you can increase the collection efficiency by this implementation of these PTFE particles. Okay, here you see such a fiber. It's also an SEM picture. Here are PTFE particles. We have evidenced the presence of these PTFE particles with EDX, with a certain method. We could see that there is a lot of fluorine here in these nodes. And now is the question how we can realize this spinning process. And I developed a lot. I made a lot of experiences, and I find out. Please remember to the spinning process. If you consider this simple lab scale trial, you have an injection of charges in the droplet, and therefore you need at least a really, really low degree of electrical conductivity to ensure that you can inject the charges into the droplet. So, but if you have PTFE in a solution or in a dispersion, you will lower the electrical conductivity. And therefore, the result is that you have to increase the electrical conductivity of such a solution. And therefore, I will give you some values. If you add PTFE particles in a range of 5 to 10% to a polyamide 6 spinning solution, you have electrical conductivity of roughly 100 microsiemens per centimeter. And therefore, you have to increase this conductivity. And what you can do is that you add some additives like this tetraacyl ammonium ethyl sulfates. And then you can increase the conductivity to roughly 1,600 up to 2,000 microsiemens per centimeter. And therefore, the result is that you achieve spinable polyamide PTFE6 solutions. And maybe why I present this topic here, it's at first really important to know that we can generate polyamide nanofibers with PTFE particles, with implemented PTFE particles. But in my opinion, this approach with this conductive additives is also applicable to other problems, to other issues. Maybe you know, there are a lot of investigations. Sometimes the people create a very good material with really good properties, like, let me say, artificial spider webs or something like this. But these material is not spinable from a solution. And maybe this approach here helps us to find a solution, to find a method for the spinning also of these solutions to generate nanofibers from this really good materials. Okay, I hope it was not so boring for the experts. It was also interesting for all of you. Thank you very much for your attention. And so I hope you have a lot of questions.
Thank you very much, sir, for such an illuminating presentation. There are some questions by participants. So very first question is, will there be any effect of spinning solutions on diameter of fiber?
We have any effects of the diameter, of course. You can increase the voltage. It's one possibility. However, if you increase the voltage very, very much, then you have every time the risk of breakdowns. And especially if you work with flammable solvents, it's a big problem. That's a big problem. And furthermore, of course, there are some other possibilities. You can also use a really low concentration of the spinning solution. However, if the concentration is too low, you will not create any fibers, you will create only powders. That's more or less electrospraying. I have seen also during my time in the development that you have often a mixture of particles and fibers if the concentration is too low. Okay?
Okay. Yeah, thank you, sir. One more question is there. What is the performance life of nanofibers as it has very low strength?
There is no general answer possible. There is no general answer possible. In the most cases, the people use polyamide 6, because it's a system which is very well known. And let me say, the nanofibers are not so often used, let me say, for mechanical applications. The main part is the sector of filtration, the field of filtration. And that's not, let me say, in the direction of the reinforcement of materials or something like this. Because therefore the process of these nanofibers is too complicated to get the nanofibers into the materials. Okay?
Okay. Thank you very much, sir. As a token of love and affection, we are presenting here with certificate of appreciation. We request you to kindly accept this appreciation.
Thank you very much. Thank you very much.
Thank you, sir. Now let us move ahead for our next presentation by Mr. Jan Thel. Mr. Jan Thel is working as a research associate at the institute from RWTH Aachen University, Germany, in the division of multifilament technology. He has completed his master's degree from Aken University. The focuses of his research are both the recyclability of yarns and textiles, as well the development of med spinning process for highly elastic yarns. Mr. Thel is carrying out research on the med spinning, on the analysis of polymers and corresponding fiber properties. Such a delightful personality is going to give presentation on challenges in the recycling of post-consumer textile waste. We request Mr. Jan Thel to start with his presentation. Please, sir.
All right, so thank you very much, Ms. Schaban, for the kind introduction. I will now share my screen. Of course, again, the question, do you see the presentation?
Yes, it is visible.
All right, thank you. Great. So yeah, welcome everyone to my presentation on the challenges in the recycling of post-consumer textile waste. Yeah, I'm really excited actually to give this presentation because the waste stream of textile waste is extremely complex in comparison to other waste streams, and therefore it is, yeah, there is a lot of research going on and a lot of things to do. And within this presentation, you will see, therefore, only a short part of the actual work that has been done to carry out recycling of post-consumer textile waste. But I think one of the most important and also one of the most interesting parts. So what will be the program for the next 25 minutes? First of all, I would like to show you how actually the recycling or the term of recycling fits into the concept of a textile-based bioeconomy. So recycling is only one of the steps or one of the paths that can be used to enable a sustainable textile bioeconomy. And how does it fit in? After that, I would like to give you an overview of the current state of the art. So how is currently textile waste disposed or recycled, and where are also some deficits where we can do research on. Derived from that, I will present you one specific process and also one specific step, and explain a little bit on that step why is there a challenge and actually how to overcome it. And finally, I would like to give you a summary and also an outlook on the upcoming topics about the recycling. So let's start with the recycling and how it actually fits to the textile-based bioeconomy. When we talk about bioeconomy or textile-based bioeconomy, we mostly talk about the renewable carbon. So anything in the textile sector we currently do is related to some kind of carbon, no matter if it's from natural fibers, so wool or cotton, or it comes from man-made fibers, for example, P2 or PA. There are some exceptions, for example, the basalt fibers, but yeah, more than 90% of any fibers have something to do with carbon. So if we want to really enable a circular economy, we have to take into the account how we can recycle or recirculate the carbon. And for that, we basically have three possibilities. First of all, we could use CO2. For example, a colleague of mine, Dr. Manvi, is conducting research on CO2-based polyurethane. We take CO2 from exhaustion gases and actually use them for the polymerization. You can also take the biomass itself. That's highly likely, of course, for natural fibers such as cotton or wool, but you can also take it, for example, for viscose if you go for the man-made fibers. And you can simply use old materials, bring them back to the circle, which accounts to the term of recycling. And actually, because textile have a wide range of applications, you see only 8 of them displayed on the bottom left. It's very complex because every application and every use of it demands different properties and also different materials. And besides that, there are some potential within the textile supply chain, which are, can be used to enable recycling. So first of all, of course, during the material process and product development, we can enable some kind of circularability. So for example, the design products in a way that they can fit to current recycling processes. It's also possible to develop specific business models, e.g. take-back systems or something like that. You will see that in a few minutes. Also important is the education and training of people, so that people know how to actually dispose the textiles, that they can be recirculated to the cycle, because once a textile is gone or leaves the path of recycling, it's very difficult, almost impossible to actually bring it back. And finally, because we don't want to actually make things worse by making it better, we always have to take into account that we do some kind of analysis on anything we do, e.g. life cycle analysis, where we actually measure how is the water consumption, how is the energy consumption, how is the CO2 emissions. Is it actually something that makes or improves the things? All right, and as you can see, it's a pretty complex topic. And today I would like to talk to you, of course, about the recycling route, but especially on the cloth text, so apparel textiles, and on the level of material, process, and product development. And for that, just one short hint: the driver of this field of research is currently the so-called fast fashion. What is fast fashion? You see here some numbers provided by the Ellen MacArthur Foundation from the UK. They carried out a study about 3 or 4 years ago on the actual problem of fast fashion. And as you can see, worldwide, as the global apparel production nearly doubled within 15 years from 2000 to 2015. And in the same time, the average use numbers before actually a textile is retired or disposed dropped by 35%. So we have a rising amount of textiles, which comes back to waste management systems in shorter times and shorter times again. So this also accounts to the actual consumption of resources. You can see the Ellen MacArthur Foundation is predicting that it will triple within the now upcoming 30 years, from 98 million in 2015 to nearly 300 million in 2050. So as you can see, the textile industry has also a huge impact on ecological questions. And this is why we are currently doing so much research on it. And now I would like to show you the current process chain of apparel textile waste management and also derive some deficits from it. So before we actually talk about textile recycling and anything in this field, it's highly important to get some definitions, because in this field, some terms are used synonymous. Also, sometimes they are used in a wrong way. So I would like to show you now 6 definitions of the European Directive 2008/89 EC, which is the basic outline for any waste policy in the European Union. And there will be some distinctions between different waste management systems, but you'll see this in a minute. So first of all, the question is, what is actually waste? So waste is basically any substance or subjects which either the holder discards actually, or he wants to discard, or he has to discard. So there are three reasons.
Hello.
Yeah.
Jantil, sorry for interruption. Your slides are not moving.
Yeah, I cannot.
PPT. Have you started the PPT? It is not, moving.
I have started the presentation. I can see anything perfectly here.
Yeah. But slides.
Yeah.
You have started. You have started showing slides.
Yeah.
Herr Thiel, Sie sind immer noch auf Seite 1. Sie sind immer noch auf Seite 1.
Oh, okay.
Gehen Sie mal auf den Präsentationsmodus, bitte. Sie müssen mal auf den.
Yeah, I'm in the presentation mode. I'm sorry. Maybe you can share it from.
Yeah, you can share it.
I will try it just one more time and then. All right, so
You can share.
Try this one. Does it work?
Yes,
Yeah.
yes.
Yeah,
yes,
it is
yes.
okay. It is
Alright.
okay. It is fine now.
Okay. Okay. I'm very sorry for this. Probably I pressed the wrong button, but yeah. So because how actually waste can become waste, or products can be waste. So any substance or object the holder discards actually, or intends to discard, or is required to discard. So there are some different drivers to actually enable waste genesis. Then there are some different ways to treat the waste. One of the most important for the apparel textile waste is actually the preparing of reuse. What is preparing of reuse? When you prepare an apparel textile waste piece for reuse, you simply check it, you maybe clean it, repair it, maybe you adjust a new button or something like that, and then you can use it for the original purpose. And this use for the original purpose is really important because by this, it's a reused textile, but it's not a recycled one. Recycling in comparison to that is that the waste actually has to be processed into some way. And by this process, you receive intermediate products, which you can reprocess to new products. And then it doesn't matter if it's the original process or purpose, or if it's some other purpose. So the recycling in comparison to the reuse, the difference is for recycling, you can have any use or any purpose of the textile afterwards. And for the preparing, you have to have the same, and you don't have to have any intermediate processes. In comparison to that, you can also have a recovery. During recovery, you actually, or the waste serves only another useful purpose by simply replacing other materials. This accounts, for example, with fuels. So, for example, if you go for thermal recovery or energy recovery in a energy plant, and you add your textile waste as a fuel, this is also some kind of recovery. In contrast to the recovery, you have the disposal. And the disposal simply is any operation that's not a recovery or recycling or preparation of use. And there the target is only to, let's say this way, to get rid of the waste. So if you burn the textiles only to let the waste disappear into CO2 and other gases, and you don't want to have energy recovery, or you go to the landfilling, this is a disposal. And all of these terms, anything that's related to the textile waste is put together under the term of waste management. So actually, when people talk a lot about recycling and collection and something like that, they basically mean waste management, but they often use the term of recycling. But recycling itself is only that one specific part of the entire waste management. All right, so let's have a look at the current process chain. With textiles, the place of waste genesis and the type of textile and quality define the way of waste management. Sometimes you have a sorting that doesn't happen to any routes. So for example, if you have textiles from the medical sector, hospitals, which are contaminated with blood, you do not actually do a sorting, you send them simply to the incineration. But for apparel textile waste, you basically have some kind of sorting. And depending on the result of sorting, you go into the different routes. I have just presented one slide ago. So you go either for the reuse, the recycling, the recovery, or the disposal. And the thing is, if you go for the recovery or the disposal line, you are in a linear system, but you will not come back to a circular one to bring it back to production. For this, actually, you need the reuse or the recycling route. And within the last year, due to fast fashion, the share has changed. So in Germany, for example, currently only 50% of the textiles are actually reused or recycled in a way that they are put back into a circle. Now let's have a look on a detailed look on the single systems. First of all, for the collection, the collection, how it's carried out, depends massively on national frameworks. So currently, the state of the art is that the apparel textiles are collected via these containers or by street collection, mostly in the bags displayed on the right. And sometimes you have take-back systems in shops where you can bring directly your textiles back to the retailers. You get some kind of refund, and then you can simply buy new clothes. Of course, they do it as some kind of customer binding to the company, but that's also one of the systems. The municipal waste is especially a route for worn out and contaminated textiles. For example, all cleaning rags usually are not put back into containers or into bags, but they're simply disposed via the municipal waste. One specific or one important requirement for textile recycling is that we have a separate collection from other waste streams. So once textiles are contaminated, e.g. by municipal waste, it's highly difficult to actually recycle them. So the European Union, for example, has set up a requirement for any member state to establish separate collection systems until the 1st of January 2024. And currently there is with some people, some panic because also retailers actually have to take back the textile waste and they don't know what to do with it. All right. Basically, you have in any waste management system a market share that's mainly between public, commercial, and non-profit organizations. For the sorting, how does the sorting work? In contrast to other waste streams, it's almost only hand sorting. So because you have to assess the variability and the fashion of the textiles, it's not possible to conduct it with machines like you can do it, e.g. for the plastics or the metal detection. And the sorting also usually doesn't happen by material, but by the type of textile. So is it a scarf, is it a shirt or something else? Of course, you have some kind of material sorting by this sorting because, for example, sports textiles mostly consist of PET or PA, but not of cotton. But that's not the major intention. The major intention is to sort it actually by type. It's basically a two or three stage process. So you have some kind of quick pre-sorting, more intensive main sorting, and sometimes post-sorting. What happens during these stages? At the pre-sorting, the bags are simply opened. The textiles are then spread out on a sorting table. And within a few seconds, the workers decide, is it a non-textile, is it a textile? And if it's a textile, what kind of textile? Is it variable or is it not variable? Up to 350 different pre-fractions, and they're simply sorted quickly into some bins, and via conveyor system, it is transported to the main sorting. And as I said, question essential, is it variable or not? The non-variable textiles go immediately to the recycling fraction, and variable textiles go to a main sorting. And during the main sorting, there is an assessment according to customer-oriented categories, and the target is to actually categorize the textiles as accurate as possible, because the collectors only receive money for the highest value categories, and this have to be very, very specific textiles. And currently in Germany, the textile collectors and sorters, they only get money for about 40 to 50% of the textiles they actually sort. Sometimes, as I said, you have some kind of post-sorting. In the post-sorting, you go back to the recycling fraction and sort it again. This accounts only to a few waste streams. So for example, for jeans or t-shirts, so textiles with a high content of cotton, because you can, for example, make cleaning rags of them. Then you check, do they have holes or do they have cuts. If they don't and they have a specific area, they are also sorted out for the production of cleaning racks. Besides that, there are some other ways of waste management. For example, the recovery. As example, in Germany, it's very common that you use the material for the backfilling of empty mines, but also as fuel in power plants. It's also, when you burn it, it's some kind of pollutant sink, so you don't enrich during the cycles some pollutants, but you can also get rid of them or make them hygienize the textiles by simply burning them into a power plant. Of course, after that, there is no more recycling possible because the textiles are either stored several meters in the ground or have emitted to CO2. On the other hand, there is a possibility of disposal. So when you're landfilling and incineration in a waste incineration plant, and for the incineration, it's the same with the thermal recovery. But for the landfilling, you have additionally some other issues. So especially greenhouse gas emissions from methane, so anaerobic processes, but also always the danger of macro and microplastic emissions simply from washing the textiles away from the landfills. All right, so now let's talk about the recycling. And if you recall, this was the definition of recycling. And current state-of-the-art technologies are the cutting into cleaning racks, also the production of insulation material and painter's fleeces by tearing, and also the production of secondary yarns. You simply cut the material down, produce the single fibers, and have some kind of rotor spinning for the respun yarn. The thing is, with this current process, it's some kind of a cascade. It's not a circle, it's a cascade, and you have always a danger of downcycling. What does it mean? For the first loop, as you can see here, it's possible to make a t-shirt into a cleaning rack. That's a recycling by definition. You can also go from the t-shirt to the t-shirt. That's also recycling by definition. But if you enter the second cycle, you can go from a cleaning rack, not back to a cleaning rack. You will go to an incineration, which is the recovery or disposal. And for the t-shirt, if it's designed in that way, you can actually go back to a t-shirt. And then you have this cycle you see on the right-hand side, but not a linear straight line as it is for the cleaning racks. All right, so now what are actually challenges in the textile recycling in particular? This is the outline for a circular economy based on recycling as it has been presented so far by the definitions. And as you can see, there is something left, the preparation. Why is it important? The preparation enables actually the textiles to go into various or different routes of recycling. You can see a short overview of here. Currently, state-of-the-art technologies are the material recycling, the mechanical, and the regranulation. And once the textiles or the products left the recycling process, you can actually design the new products and bring them to the market. In this presentation, I would like to focus only on the material recycling and the regranulation route, because, of course, I'm from the melt spinning department, but also more than 60% of the produced fibers every year are currently made of PET or PA, which are melt spun, and so they can be fed by regranulates. And what are the specific challenges in the use of regranulates? First of all, we have a vast majority of mixtures of fibrous materials. So for example, for a t-shirt, you can have polyester cotton mixtures on fiber level. So you have cut staple fibers from PET multifilament yarns. In the spinning process, you mix it with cotton, and you will never ever receive the PET or the cotton in a very clean way back. So this is one of the major challenges, these material mixtures, how to overcome them. We also have a lot of multi-layer constructions and trims, especially for jackets or protective clothing, which correspond to different materials. I will explain in a minute what the specific problems are. Additionally, we have additives and dyes in different textile parts and layers, which means the additives, for example, can lead to filter blocks, and the different colors make it almost impossible to obtain one specified color in the end of the recycling process. So let's have a look at the removal of interference, and let's have a practical example. Over here, you see the worst case of textile recycling. That's an outer jacket. With an outer jacket, you have usually zippers made of POM or metals. And if you want to carry out material recycling by regranulation, you have to get rid of the zippers. Why? Because they are either made of metals or POM. Why is it a problem? The POM, if you bring it to the regranulation process, it's a plastic, but during the regranulation, it will formulate formaldehyde, so a toxic gas, which we must not have in our process. If you go for metal zippers, the problem is it will highly likely damage machinery parts, e.g. the screws of the extruders. You additionally have labels, which also account for the risk of incompatible materials and incorrect labels, because the material of the labels, it's not separately declared on the label what the label is made from. And depending on the material, it also can interfere with the regranulation process. Additionally, you have, as I said, highly likely with these outer jackets, different material for inner and outer parts. So for example, the inner parts, the linings are made of PET, the outer parts are made of polyamide, and sometimes they are even, there's even more different textile fiber types. So for example, elastanes, which also come from different fiber production processes. So for example, the elastic parts of these textiles are mainly dry spun elastane, and this dry spun elastane cannot be retransferred to a melt spinning process. So there's also not only that you have different materials from the same production process, but also from other production processes. Sometimes you also have coatings and additives which interfere with the regranulation and also with the melt spinning. For these outer jackets, it's, for example, pretty common that you use PU as a water repellent part. So the PU will highly likely degrade before it actually melts. So it cannot be refed to the recycling stream. All right, just quick, I know the time is running. Just quick, what are the possible applications for regranulate? We, of course, want to go to the textile way back. So we can most likely produce pure multifilament yarns from regranulates in a proper quality. It's also possible to cut the yarn later on and use it as a staple fiber, for example, for the blending with cotton. We can also go to the monofilament route. This is also likely for the production of fishing threads. So there are some ways. Additionally, if you don't want to go to the textile routes back, you can use it for films or tapes or foams, and of course for the injection molding. But that's always the last way you should go, because then you are no longer into the circle. And now I'm coming to the conclusion. So as you have seen, the reasons for textile recycling are ecological, of course, but they are also economical. As you can see, currently the market prices for the plastics are rising. So if you are able to actually get or retrieve material back that has already been processed, it can also be some kind of financial advantage. Additionally, you have just obtained some knowledge in the terms of waste management. So maybe next time if you hear something in the context of recycling, you know that it's actually not recycling that you're talking about, but maybe the collection of the preparation for reuse or some other terms. The current textile waste management system is a linear one, and for the transfer to a circular economy, some challenges have to overcome. especially in the design of products and processes and materials, but also for the education and training, and also for business models. The growth of the fiber production is currently mainly driven by man-made fibers, especially PET and PA, which account currently to more than 60% of the worldwide produced fibers. And yeah, the environment impact of the textiles will increase massively in the coming decades, especially due to the population growth and also the growth of wealth all over the world. All right, and with this, I would like to finish my presentation, and I'm looking forward to your questions. Thank you very much.
Thank you. Thank you very much, sir, for throwing light on recycling of textile waste. There are some questions by participants. So very first question is by Pradeep Hamsa. What about recycling of man-made fibers?
Yeah, basically, man-made fibers, in my opinion, they are a great source for the recycling. So, as I said, it's desirable to go for the regranulation route, but you have to have very clean content. So it shouldn't be done that you actually mix the man-made fibers. So, for example, you have a PET and PA mixture, to some extent, it's still possible to have some kind of blending afterwards, or regranulate that are blends. But if you go, for example, for PET and PE, you also have man-made fibers, but they are completely different in the processing. So the PE has a way more lower melting point, for example, and will highly likely degrade earlier. So that's not possible to mix it. But if you go for the man-made fibers, you should have clean products, let's say this way, monomaterial products. And then it's actually possible to carry out the regranulation and the respinning. So we have, at our institute, we have already done trials with regranulates coming from man-made based textiles, but they have also post-consumer, not only production, but they have to be designed in a specific way that I mentioned before. I hope this satisfies your question.
Thank you, sir. One more question is there by Mr. Dinesh. How do you do segregation of blends like polyester cotton blend, polyester wool blend? Yeah,
that's the thing. So currently there is a lot of research going on this. The processes I know so far, which are also state of the art, they do not separate them. So they simply cut it and use the fibers for something else, e.g. for these painter's fleeces. There are some ideas to go there with chemical processes, but these processes always the work in the lab scale, but for the industrial scale, so far either they do not work or they are too expensive. And the thing is, with the textile waste, or if you go for the regranulation route, for example, it's possible to carry it out with only a small amount of textile waste. So you can have your regranulation plants everywhere. It's a simple logistic, but if you go for these big chemical processes, you have to have very huge throughput, several dozens of tons of material every day that have to be fed to the plant. And this is also a logistical problem to carry it out. So yeah, as I said, once it's blended, for example, during the rotor spinning, it's almost impossible to retrieve the cotton or the PET back. It's possible on lab on pilot scale, but it also takes a lot of time, and it's very, it costs a lot of money. And if you take into account 1 kilogram of PET fiber is something between 1 and 3 euros, of course, depending on the process and the yarn itself. So there is not much space for expensive processes. So I hope this also satisfies the question. So from our side, it's always highly likely that we have these monomaterials.
Yeah, thank you. One more question is there by Mr. Kiran Ranade. What is the whiteness index can be achieved from recycled polyester filament or fiber?
I'm sorry, I didn't understand the question. Could you repeat it, please?
What is the whiteness index can be achieved from recycled polyester filament or fiber?
The fineness of the yarn.
Whiteness index. What is the whiteness index? Sorry, there was some interruption due to network issue. So we will post rest of the questions to you through email, and the answers will be shared with participants. So thank you very much, sir, for your such an explanatory presentation. As a token of love and affection, we are presenting here with certificate of appreciation. We request you to kindly accept this appreciation.
Thank you.
Thank you very much. Now it's time to move for our next technical presentation by Professor Dr. A.K. Patra. Dr. A.K. Patra is Professor and Head Textile Chemistry in Textile Technology Institute, Kanpur, India. He had just completed his term as Dean Academics. He has completed PhD from National Institute of Technology, Punjab. He has professional experience of more than 28 years. He is having large number of publications in various national and international journals and is a reviewer for Sage publication and elsewhere publication. He has presented research papers in various conferences and also had chaired technical sessions in international conferences and had been a panelist in Bioeconomy 2016 conclave. He is a fellow of Society of Dyers and Colorists UK. He has handled many research and consultancy projects as well. Such an inspiring personality is available with us for presenting a paper on topic Chemical Management in Wet Processing the Responsible Way. We request Professor Patra to start with his presentation. Please, sir.
Thank you. Thank you for the generous introduction. Let me just share the screen first. Yeah, is it visible?
Yes, sir, it is visible. Switch to presentation mode.
Right.
Please. Yeah, it's visible.
It's clearly visible, right? Okay, thank you. So I'll be discussing about chemical management in wet processing. So it's a little different from the topics that have been discussed since morning, and it's core textile chemical processing, but not the traditional chemical processing, but what is new happening and mainly the chemical restrictions we have now coming up globally and how important it is. So those are the attributes which we will be discussing. And we have fair number of student participants, as I see. So probably that will be of great interest to them. And before I get on with the subject, let me just briefly introduce my institute. So I work for UP Textile Technology Institute, more popularly known as GCTI Kanpur, which is in the northern part of the country. So the institute is a century-old organization, started in 1914. And 1937, it got the name Government Central Textile Institute. 1914, it started as School of Dyeing and Printing. Then 1937, it was Government Central Textile Institute. And in 1958, the 4-year degree course started. Before that, it was diploma, as in many of the institutions across the country you see. And 1966, it was affiliated to the Kanpur University. Then 76, the man-made fiber technology branch was started. And in 2005,
textile engineering branch was added. So now we have 4 different textile branches: textile technology, textile chemistry, man-made fiber technology, and textile engineering. And we offer UG, PG, and doctoral courses. And the exclusivity is that we are the only institute in the country which offers only textile courses. We have no other courses but textiles only. And we organize annual international conferences regularly. And these are some of the glimpses. We had the annual conference under the name Advances in Textile Materials and Processes in 2018, 2019, and with a sizable presence of scientists and researchers from abroad as well as from our own country, India. And I was the convener for both the conferences. Because of the pandemic, of course, now we have not been able to do this, but there are a few online conferences we have been doing on a yearly basis under a different name. So with that backdrop, let me get on with the subject that we are to discuss. So starting with the historical background, traditionally in any industrial practice, whether it is textile or non-textile, the emphasis has been on cost and then the quantity of production and subsequently the quality of the product. As far as textiles is concerned, the impact of textile manufacturing on the customers, workers, and community and environment have somehow been accorded a lower priority. And the main input in textile processing, as we know, is the chemicals that we use. So gradually it was found with passage of time that some of the chemicals are really hazardous and we need to restrict their uses. But initially the classification was mainly under the term toxic, which used to cause death mainly through oral, dermal, and inhalation routes. But later on, it has been found that there are many endpoints through which the hazards can happen. It can be, say, neurotoxicity, it can be reprotoxicity. So likewise, so the domain has now substantially increased, and the research level has also gone up, and so also the restrictions by different statutory bodies. As you know that the various chemicals we normally use, they are listed under the Chemical Abstract Services, that is CAS. Now in CAS, we have about 4 million substances registered across the globe. And interestingly, only the impact of 20% of those are known. 80% of those which are listed, we don't know their impact on human health. And in fact, the major breakthrough came in 2010 when a global NGO called Greenpeace, they, after surveying 2 major processing units in China, they came up with a report called Dirty Laundry. And that opened up literally the Pandora's box, showing that the amount of waste liquor coming out of these process houses and the toxic chemicals it contains, like APO, alkyl phenol ethoxylates, then phthalates, and ultimately those waste liquors or wastewater was going to the rivers, ultimately polluting the water bodies and causing serious hazards to aquatic life as well as to the human health who are ultimately consuming it. So as a response to that, the very next year, 2011, ZDHC came into existence, that is Zero Discharge of Hazardous Chemicals, and major textile, apparel, leather, and footwear manufacturers, they came together as a response. And the ZDHC came up with a list of these restricted substances, the substances which are not to be used, under the term MRSL, it is Manufacturing Restricted Substances List. And this was published sometime in 2014, and now we have the newer version published in 2020 under the name MRSL 2.0. Then other than this, many brands, say like Nike or H&M, they have their own list of restricted substances. And as manufacturers, we need to follow that. Then you have the Global Organic Textile Standards, GOTS, which is the latest version, 36.0. We have GOTS 1, 2, 3, 4, 5, and now it is 6, which covers the processing, manufacturing, packaging, labeling, trading, and distribution of textiles. Other than that, we have a firm that is Apparel Footwear International RSL Management Group, which was of course established way back in 2004. And they also have their list of restricted substances. In fact, there are two things. One is the MRSL and the other one is RSL. So MRSL is the manufacturing restricted substances list, which would mean the chemicals which are not to be used during manufacturing. Say, for example, in scouring, we use wetting agents. So the wetting agents that we're using may be containing APU, that is alkyl phenol ethoxylates, which are very much hazardous to aquatic life. So they should be APO free, right? So that is about the manufacturing restricted substances list. Coming to RSL, it mainly relates to the substances that are present on the textile material. So what is present on the textile material that we're going to use? So RSL mainly refers to that. So MRSL would mean that it covers the environmental aspects, it covers the wastewater liquor, and of course, finally, the product that is going on the material. Whereas RSL mainly refers to the substances that are present on the textile material, right? So these are some of the restricted substances, and you can see the list. Just excuse me for a while. There was some disturbance from outside. So here, if you see the restricted substances, you have alkyl phenol and alkyl phenol ethoxylates, which I was talking about. Then we have the azoamines and arylamine salts, then bisphenols, then chlorinated paraffins, chlorophenols, carriers, then dimethyl fumarate, forbidden dyes, likewise. So there are many, and I'll not be discussing all those due to the paucity of time. So only a few I'll be discussing. Now coming to the alkyl phenols and alkyl phenol ethoxylates. So here, if you see, APO is basically a non-anic surfactant or detergent or wetting agent, which we very commonly use. Wetting agents are very commonly used in scouring, in bleaching, in even dyeing and printing as well. And these APOs have also dispersing, antistatic, solubilizing, and lubricating properties. If you see the figure here, it shows clearly that say when something is not wettable, then you have an say critical angle or the contact angle which is much higher, which is obtuse, and gradually that decreases. And when you go to the right, you find that here there is excellent wetting. Okay, so wetting agents are something which are almost like an inevitable part of the textile processing, as you know. I'm just trying to move to the next slide. Okay, so in this we have two components. One is the alkyl phenol part, and the other one is the ethoxylate part. Now, in this alkyl phenol part, it is in fact non-polar and it is lipophilic. Lipophilic means which is oil loving. Okay, and that in fact allows dissolution of greases and all such impurities. And the ethoxylate part is responsible for water solubility. And in this alkyl phenol part, it is mainly nonyl phenol, which is very widely used commercially, and then next to that is octyl phenol. The disadvantage with these chemicals is they're acutely toxic and endocrine disruptors. Endocrine, as you know, is a gland, so this can cause endocrine disruption. Then estrogenic, which is again related to the hormonal aspects, and carcinogenic as well. So a lot many disadvantages with this, and particularly it has got a very strong negative impact on the aquatic life, more on aquatic life than the human life. And many of these fishes, they have slight genetically changed behavior because of this. So the male fish may tend to behave like a female fish. So that is the extent of damage it causes. And the alkyl phenols or the nonyl phenols are in fact the biodegradation products of the alkyl phenol ethoxylates. Okay, so the total product that you have that dissociates to alkyl phenol and to the ethoxylate. And that alkyl phenol is in fact responsible. The ethoxylate doesn't have any problem. So the figure here, the figure shows how it can be problematic. And if you see here, this is the alkyl phenol part, benzene ring, and here you have the OH part. So this is the phenolic part. R is alkyl. Okay, so the nonyl phenol I was telling, this R is the nonyl phenol part, which can be C9H19, or it can be octyl, that is C8H17. Okay, so this is the alkyl part. So this whole thing is alkyl phenol part. And here you have got the ethoxylate part. So that is nothing but ethylene oxide. So here you have CS2, CS2O, say M number of this, followed by the final N. Okay. Now this may dissociate to finally form, you have got many intermediate products, and finally what is formed is the alkyl phenol. And this alkyl phenol is very risky. Okay. And the problems that we discussed is mainly caused by this alkyl. So the option is to avoid the use of these alkyl phenols in wetting agents, and that will serve the purpose. Ethylene oxide doesn't have any issue at all. Okay. So there is an example, say 4-nanyl phenol, it mimics the estradiol hormone and this affects development. So it is again affecting the
I think there is some problem at speaker's end, some network issue. Please wait.
Hello. Hello. हे काय आलं?
Hello. Sir is rejoining. Please wait for a while. Some internet issue is there at speaker's end. Participants, please wait. Sir is joining soon. Within 2 minutes, sir is joining. Please wait. Sir had joined. Sir had joined. We'll start very soon.
I've just joined. Sorry for the interruption. So I'm sharing the screen now. Okay, so normally there is no electricity failure, but somehow it happened now.
Yeah, no issue, sir. You
So-
may start, sir, please.
Yeah, so I was talking about the alkyl phenol
Yeah,
ethoxylates,
please,
which are normally.
sir, sorry for interruption. Please, can you start it in presentation mode, please?
Yeah,
And your video also, please, sir. Please turn on your video. Yeah, it's visible now.
right.
Will you please turn on your video, sir?
Yeah, that is what I'm doing.
It's okay, sir. Fine.
Okay, sorry for the inconveniences caused, a situation which is not within my control. So the APU I was talking about, we have now alternatives for that APU, which is definitely a newer thing. And you can have these APUs substituted by alcohols. So instead of the alkyl phenol, you have alcohol. So you have a combination of alcohol and ethoxylates. So this you can see here in the figure below. So here you have the ROH, okay, so that is the alcohol, and R is the alkyl part. So it may be C9 to C11, and then you have the OH, and then this is the ethylene oxide part. So n number of ethylene oxide parts. So finally it combines to form this alcohol ethoxylate. Okay. So this is one product which is now being used very commonly. So you have the wetting agents from Huntsman like Ultravon ECP or the CeraVet CS from Dystar. These are all APU free. And the main product in that is the alcohol ethoxylate. Okay. Then coming to the next restricted substance, which is the azoamines and arylamines. In fact, the azodye ban started in 1995, so it's more than 25 years, and the ban started in Germany. At that time, there was a lot of discussion, a lot of confusion also arising out of it, and there used to be articles like who is confusing whom. There was a confusion that probably azodyes are banned, but that is not the case. Just for clarity, azo is a chromophore which is very widely used in most of the textile dyes. And you have about 2,000 azo dyes in the market available. And out of that, only those azo dyes which on reductive cleavage form amines, which are carcinogenic in nature, only those azo dyes are banned. So in total, there were about 118 dyes which were found to reductively break to form such amines. And in fact, those azo dyes are only banned. Rest of the azo dyes are absolutely free of any problems, and they can be used, and they are also in use. Okay. So the 118 dyes which were banned, they were in fact spread over 6 different classes of dyes, like the direct dyes. Some of the acid dyes were banned, and dispersed. A few basic dyes were also banned. However, no reactive dyes came under this, so they didn't have any problem at all. And as you know, that reactive dyes are very widely used in textiles. Now, in this, the problem with the azo, this is the scope of the product. So you may have, because dyes are very commonly used on all textiles materials. So it can be the clothing, it can be say hair pieces, it can be hats, nappies, it can be jackets, it can be caps. All these materials are likely to have presence of those forbidden amines if we are using those banned azo dyes. However, that is almost now out of the market, so we don't have much of a problem. And the azo dyes I was talking about, these are the amines which are carcinogenic in nature. They can be confirmed carcinogens, or they may be suspected carcinogens. Okay, and the equation that you see at the bottom, This shows that this is a dye which has got N double bond N, which is the azochromophore, and that on reduction may form these two amines. And if this amine is carcinogenic in nature, then actually this dye cannot be used. So only such dyes are not to be used. Then we have the other one, that is the bisphenols, and I'll not go much into details of this due to the paucity of time. And bisphenol, if you see that typically the structure, you have got two phenols here, and then in between you have this. So it can be bisphenol A, it can be bisphenol S, F, AF likewise. So in fact, this part changes. It may be say H, or it may be say sulfur, likewise it changes. Okay, and they may be found in polycarbonate bottles and food beverage cans and all that. So particularly babies, for their say feeding and all that, the milk is kept in bottles. So those bottles may contain bisphenol. So that is something which is to be very carefully monitored. And then we come to the chlorinated paraffins. So chlorinated paraffins, again, simple paraffin structure. So you can take an alkane structure, as you see here at the top, and then it is chlorinated. Okay, so it can be a short chain chlorinated paraffin, or it can be a medium chain chlorinated paraffin. And short chain chlorinated paraffin normally have 10 to 13 carbon atoms, whereas the medium chain have 14 to 17 carbon atoms. Okay, and the chlorine content in both the cases is about 40 to 70%. Now these are toxic to aquatic organisms and may cause long-term adverse effect on the aquatic environment. Okay, and certain exposure levels may even cause problem to human health. And these short chain components, they are also a candidate list for SVHC. Students may take a little careful note of this. You have substances of very high concern, and it is called SVHC under REACH. REACH is, as you know, is one of the major bodies for European Union, mainly focusing on these restricted chemicals. So this is again a candidate for that, although it is not listed, but it's a candidate in the offering, right? And repeated exposure to these products can cause problems like irritation, toxicity in human beings, and all that. So they have to be carefully monitored, particularly in synthetic leather, polymeric coatings, and all that. And textiles and plastic materials treated with flame retardants may also contain these. Okay, and few minutes back, as I was talking about AFFIRM, that is the Apparel Footwear International RSL Management Group. So they have restricted its limit to 1000 ppm, and anything more than 100 should be reported. Then we come to chlorophenols. Chlorophenols is something which is a culprit we know from decades, particularly the pentachlorophenol, which is a very well-known culprit we know. And these pentachloorophenols are even banned in India, even since I think early 90s. And the pentachlorophenols, the problem with them is they generate dioxin, and dioxin is one of the most polluted substances. Okay, so this is the pentachlorophenol. So you simple benzene ring with 5 chlorines, so pentachloro, and this is the phenol part, so pentachlorophenol, and this can generate dioxin, and that is why pentachlorophenol is banned. Okay, and the limit is very, very less, 0.05 ppm, as you see, milligrams per kg. So if you convert it, it is parts per million ppm. So it is almost completely not to be used. Okay, then you have got biocides. So biocides normally used in the antimicrobial finishes, and you have, say, like triclosan, which is used in our toothpaste, and triclosans are also used in mouthwashes and all that. So the usage of that is also discouraged. And dimethyl fumarate is one particular biocide which is very much discouraged to be used, because as you see the kind of effects here at the bottom, it causes redness, burns, and all those. So that is why this is something which is not to be used. Phthalates, again, a major restricted substance. And if you see the structure here at the top right, So this is the typical structure of phthalates. So these are basically esters of phthalic acid. So if you see phthalic acid here, instead of R, you have H. Okay, both the cases. So that is typically a phthalic acid. And these are esters of the phthalic acid. So that H is replaced by R. So you have the RCO, R' form. So that is nothing but ester. Okay. And they are often used in the plastic or rubbery material which are there on the t-shirts. So you have got prints like this. Okay, the second figure that you see here. So these can be a problem. And in fact, the difficulties associated with phthalates is they're bioaccumulative. Okay, so they can accumulate and the concentration doesn't go down. And they are also endocrine disruptors. Endocrine, as you know, is a gland, so it affects that, and it can be also carcinogenic. So there are in fact different types of phthalates. You may have like dibutyl phthalate, or you may have DPP, you may have DPHP, and all that. So there are about 20 different types of phthalates, and these phthalates are something which are to be avoided. And particularly in the plastic materials, like flexible materials which we have on the t-shirts or fancy effects, then on the rubbery materials, these phthalates are likely to be present. And these are some of the products which show or which are potential areas where there is a possibility of phthalate presence. However, the manufacturers who supply to the known brands, they have to ensure that the products are completely phthalate free. Okay. And the interesting part is not that we use such chemicals which cause phthalates. Phthalates may be present even in common substances, say like in acetic acid, or maybe in say compounds like sodium carbonate, sodium bicarbonate, sodium chloride, that is common salt. So these are very widely used in processing. Okay. And this is an interesting data which was in fact revealed by Ninkertech, and they found that some of the normally used chemicals also have these phthalates. Now you may question why a compound like say an acetic acid or say sodium carbonate and or say common salt that we're using in industry will have phthalates. Now the possibility is if the recycled material is used, although we talk a lot about the recycling, we talk about circular economy and all that, but then that is also not free from hazards. So if say in an acid slurry, in an acetic acid, if you have used acid slurry, then that acid slurry is nothing but a reused material. So there, although you are using that acid, but then it may be containing contaminants which it has inherited from the earlier usage. And the acetic acid, which is a very simple substance, may even contain those phthalates. So that is something which is to be ensured. And in fact, one of my friends who is into chemical manufacturing in Mumbai, I was asking him how you really manage this, and the answer was that the suppliers, the raw material suppliers to them, they have to ensure that the substances they're supplying for the chemical manufacturing should be free from all these restricted substances. So they take a declaration from them, and that is how the absence of these chemicals are completely ensured. And that is how you can comply to the MRSL I was talking about, that is the manufacturing restricted substances list. Because if you're supplying to the well-known textile users, say if you're supplying to Nike or H&M, say Marks and Spencer and all that, you must ensure that these chemicals are not there in your product. Okay. And if you want that not to be present in your final product, you also need to ensure that the chemicals that you're using also don't contain them, right? Then coming to formaldehyde, this is something which you all know, so I'm not going much into details of this. The only thing is, you should remember that when you inhale formaldehyde, there is a possibility of formation of formic acid and carbon dioxide in the upper part of the respiratory tract. And that in fact can cause serious nasal and respiratory irritation. In fact, I had a publication on this formaldehyde in Man-Made Textiles in India in 1999. So their detailed description about the formaldehyde problem and the alternatives have been discussed. So formaldehyde, as you know, causes the skin irritation, that is dermatitis, which is a skin disease which is caused by formaldehyde. And formaldehyde can be from different sources. It can be from the dye-fixing agents. One of the major sources is a anti-creasing agent that we use, the DMDHU based and all that. So there, in fact, one needs to be a little careful that the formaldehyde content is very low. Okay, it may not necessarily be zero other than baby wear. If it is low, then it is acceptable. And an alternative to this is to use BTCA, which is butane tetracarboxylic acid. And you can also use citric acid, which are both these are polycarboxylic acids. Okay, so polycarboxylic acids can be used. But the problem of using polycarboxylic acids is BTCA is very expensive and not easily available. Citric acid, as you know, is very easily available, very environment friendly. We use it in food materials also, but the problem is citric acid is a tricarboxylic acid. So 3 carboxylic acid groups are there in that, and it doesn't give adequate cross-linking. So we need to use a combination of BTC and citric acid to actually get the desired end result. Again, say heavy metals. So there is a real shortage of time, so I'm skipping this. Only thing is the heavy metals, particularly the cadmium, mercury, lead. These are the major irritants. Other than that, chromium, cobalt also have to be limited in content. Then we have PFCs, which are very widely used, and they are particularly used for water repellency and oil repellency and all that. In PFCs, we have 2 categories. One is the perfluorinated chemicals and the other one is polyfluorinated one. So perfluorinated would mean here there is a complete replacement with fluorine. Okay, so if you see the structure, you will find that it is complete replacement. So you've got the carbon chains and to that is linked fluorine. Whereas in polyfluorine, fluorinated chemicals, you have some of the substitutions by fluorine. Okay, and they come under the persistent organic pollutants, which is known as POP. So persistent means it is biopersistent. It will not decrease in content, and for its complete elimination, it will probably take years to be completely removed from the environment. So that is a problem with this, and it is not biodegradable. Okay, so Nike in 2015, as you know, Nike is a very well-known sports equipment and accessories manufacturer. So though they made a commitment in 2015 that the C8-based PFCs will be eliminated. C8 would mean you have got 8 number of carbons in that polyfluorinated product. Okay, so now you find it is mainly C6 which is being used, and if you see the byproducts of this, in fact, there are 2 ways of manufacturing PFC. One is the electrofluorination and the other one is telomerization. So electrofluorination leads to the byproduct that is perfluoroalkyl sulfonates, and telomerization, which is perfluorooctane sulfonates. Okay, sorry, it is the perfluorooctanic acids, that is PFOA. So this is the typical structure of PFOA, which is the byproduct during the manufacture of the perfluorochemicals. And as I've mentioned, C6 chemistry is now being used by most manufacturers because that is less hazardous compared to C8 as on date. But ultimately, this is also biopersistent. So maybe after some years, even the C6 will also face the restrictions. So now most of the manufacturers you will see, they supply and say that we are using C6 chemistry. But C6 chemistry is right now acceptable, but I apprehend that probably in years to come, even C6 will also have a problem. And if you use C4, the problem is it doesn't react so easily. Okay, so you require very extreme conditions, you require very high temperature conditions for the curing. And again, it is very easy to avoid a particular compound, but it is very difficult to find a substitute. Finally, the volatile organic compounds. So major volatile organic compounds are benzene, carbon tetrachlorides, chloroforms, and one of the typical feature with these is they combine with nitrogen oxide in the air, and they form smog. So that is a problem with these volatile organic compounds, and you find these maybe say in adhesives, then dry cleaning fluids, air fresheners, and all this. Although the manufacturers are taking enough care for the VOC-free products, but one has to be on the lookout. Okay, and they are restricted because of the reasons that is mentioned here. It can cause drowsiness, dizziness, headache, and chronic exposure can even cause damage to the nervous system, liver, and kidney. And as I was telling that they form smog. Say if you use toluene, then that can cause smog, which has adverse effect on human health and can damage forest and crops. So overall, if you see, these chemicals have, many of these have effect on the aquatic life, many have on the human health. So hence there is a call for restriction. And now this is being pursued very aggressively. And in industries, there is no way out. You have to follow it or you have to quit the business. Coming to the final slide, the epilogue. So often we say that the pollution is causing death and all that, but if you go figuratively, you have about 4.2 million deaths per year globally due to stroke, heart diseases, lung cancer, acute and chronic respiratory diseases caused because of the air pollution, right? Water pollution, the one that I was referring to when I was talking about the Greenpeace report. Water pollution mainly causes the destruction of biodiversity. The aquatic life is very severely affected. So that is a problem with that. And with the rising awareness and strict restrictions by brands, the industry is literally in a do or die situation. And you have ZDHC, you have got REACH, you have got GOTS, you have Affirm, and they have now a visible impact on the industrial manufacturing process. So a further development over ZDHC is now ZLD, zero liquid discharge. And as I've mentioned here, it's the new normal. So the state of the art industries or manufacturing industries and textile processing, they are coming now are ZLD, okay, zero liquid discharge. So see the transformation. We know textile processing to be a very water intensive process. And now we are coming to a stage where not even a single drop of liquid will be coming out of the industrial manufacturing unit. So that is the requirement in the present times. And responsible chemical management is therefore the need of the hour. And I end up with the sentence that we have not inherited the earth from our parents, but we have borrowed it from our children. So we need to be very careful so that the environment remains intact, and we have only one earth to live, and that is also debilitating. So we need to take extreme care to maintain the environment and ultimately also the human health. Okay, so thank you very much.
Thank you very much, sir, for such an informative presentation about chemical management. There are some questions by the participants.
Yeah.
Very first question is, sir, we are speaking about auxiliaries and chemicals used in very small quantities. What about the basic chemicals like caustic used in huge quantity and highly polluting our land?
Sorry, just repeat it.
We are speaking about auxiliaries and chemicals which are used in very small quantities. But what about the basic chemicals like caustic used in huge quantity?
Okay. The restricted substances I talked about have certain specific hazardous impacts. Okay. Now coming to the basic chemicals that we're talking about, yes. Say for example, if you're using caustic, that causes strong alkalinity. Okay. And disposal of that wastewater is also a problem. So now, in fact, the bioscouring is coming up, and probably in a decade or so, you will not see the conventional scouring taking place, and you will find bioscouring, which is with enzymes. Enzymes are biodegradable, and that is going to probably substitute the conventional scouring. So in a decade or so, probably you'll find that the textile chemical processing has got a totally different hue compared to what it has been since last so many years. So as far as caustic replacement is concerned, and in textile pre-treatment and scouring, we use a lot of caustic. So the best way is to go for bioscouring. Many of the companies like Novozymes and all, they have already come up with those formulations. So it is only for the industry to accept it. Right?
Thank you, sir. One more question is that how to check the presence of band amine in dyes?
Okay, so in fact, there are tests like HPLC, PLC, and all those specific tests by which it can be done. Okay, so you have sophisticated instruments for that, and we have laboratories who are involved in it. Okay, so you can procure those. In fact, for all these impurities which we are talking about, they have specific test methods, and that has to be followed. Okay. So the normal laboratories may not have those test equipments, but say those who have got the GCMS, HPLC and all that, they can find it out. So that is the way how to find out, right?
Okay, thank you, sir. Due to time constraint, we shall take up all the questions, or we can share the questions to Patra sir. Later on, the answers will be shared to the participants. So thank you very much, sir, for such a valuable information. As a token of love and affection, we are presenting here with certificate of appreciation. We request you to kindly accept this appreciation. Thank you, sir.
Okay, thank you very much. And sorry for the interruption which was caused inadvertently. And I'm also sorry for standing between you and your lunch, because we're already getting late.
No problem, sir. Yeah. Now we have come to the end of today's session. Be connected with DKTE family with different social media platforms. We enjoyed the learning by eminent speakers of this virtual conference. Tomorrow, again, we will continue the conference with technical sessions sharp at 9:45 AM. Kindly join using the same link as that of today. We request all the eminent speakers and participants kindly put on your camera on so that we can capture the screenshot. Please turn on your video.
Okay.
Screen.
Hello. Hello. Hello.
Yeah, participants, please turn on your video. Thank you one and all. Tomorrow again we will meet at 9:45 AM. Everyone is requested to join sharp at 9:45 AM. We'll enjoy the learning process. Thank you one and all.
Thank you.